Howdy friends, welcome back. It's great to be hanging out again. In today's masterclass, we hear from a variety of expert voices on all things metabolic health. What is metabolic health? What is metabolic flexibility? Why do people develop metabolic conditions like type 2 diabetes and non-alcoholic fatty liver disease? How specific types of exercise and nutrition can improve metabolic health, and much more. In this episode, you'll hear from Professor Inigo San Millan, an expert in exercise science, metabolism, and mitochondrial function, Professor Don Layman, an expert on all things skeletal muscle, Professor Roy Taylor, an expert on type 2 diabetes, who's very well known for the twin cycle model that we'll learn about, Dr. Andrea Glenn, who researches how different dietary patterns affect risk of developing metabolic conditions like type 2 diabetes. Dr. Alan Flanagan, who's a nutrition scientist that is very well versed in the way that different nutrients affect the health of our liver and thus metabolic health. Dr. Richard Johnson, whose research is focused on fatty liver disease and insulin resistance. And of course, crowd favorite, Professor Christos Mantzoros, a nutrition scientist and endocrinologist interested in assessing, preventing, and treating metabolic health related conditions. This is really a treasure trove of information. Please enjoy. What is your definition of metabolic health, and why should the listener care about this?
Yeah, that's a good question, and I think this is something that we're understanding more and more, right? As you know, and many people know, right? The traditional definition of metabolic health is the compendium of the multiple parameters like your lipid profile, your blood pressure levels, your glucose levels, right, and your body mass index, or at least your waist ratio. So circumference, sorry. So, but as we know more at the adaptations or what happens at the cellular level, right, we are getting to an inflection point in the field of medicine where metabolism has gone from being the poor brother to being the crown prince, right? I mean, you look at the curriculum of medical schools, even still today, they barely have any courses, right, or notions of metabolism at the cellular level. While at the research level, the advances have been immense that we can already use to help people, as well as to understand diseases at a level that we have never been, right? So this is why metabolic health implies more mitochondrial function, implies also more fitness, implies longevity, right? So people nowadays are not happy just to have good cholesterol levels, right, or good blood pressure, right, or good A1C or glucose levels, right. People want to be fitter, want to live longer, not necessarily in the amounts of years, because we all want more, but to live better, right, and want to be healthier. So all this, I would put it in the new basket, if you will, of metabolic health.
A lot of your work seems to focus on how efficiently we can take the I guess potential energy in food, be it carbohydrates or fat, and turn that from chemical energy into a mechanical energy, contract the muscle and move the skeleton. Do you also consider sort of fuel partitioning? You know, I'm interested in some of Professor Roy Taylor's work. I'm not sure if you're familiar with him and his work looking at type 2 diabetes and this concept of personal fat threshold being sort of integral to metabolic health, in that once we kind of spill over or store fat beyond our subcutaneous fat capability, it starts to get in between and within organs, and that seems to also be a sort of key component of metabolic health.
Yeah, absolutely. There's no doubt about it. That's a big component. Abdominal fat is highly associated with a cardiometabolic disease, and also there's more and more research. One of the leading researchers is my colleague here at the University of Colorado, Dr. Brian Bergman, with his research in the intramuscular fat, which is highly, and others, right? They've been doing research, extensive research on this, linking that intramuscular fat with insulin resistance and type 2 diabetes as well. So yeah, definitely fat. The connection between fat and metabolic diseases is there for sure. And we are doing already in our laboratory, and which we can talk in more detail later if you want.
Sure. How much of your understanding of how exercise specifically influences metabolic health has come from your work with elite athletes? And why are elite athletes sort of a good model for studying metabolic health?
Yeah, that's a great question. Thank you. So I always say it's difficult or not very, it's difficult to understand imperfection if we don't know perfection in the first place, right? So and elite athletes are the perfect machines. They are perfection, and they're the Ferraris or the Lamborghinis, right? So from the lessons that we have learned from working with the perfect machines, we can understand or have a reference of what perfection is, so that we can understand imperfection. So this is why I've been trying to bring for a couple of decades into the clinical space, right? To try to understand, to try to bring the lessons that we have learned working with elite athletes, so that we can understand different diseases better, as well as the application of different interventions like exercise, especially, and also even nutrition.
How much of the sort of cardiometabolic disease burden that we see today do you feel is explained by sedentary lifestyles and a lack of specific cardiovascular training versus other things like nutrition, which you just mentioned?
Yeah, so I'm going to wear my cell physiology background, right, and try to see this from a decrease in mitochondrial function or a decay in the mitochondrial function. So the mitochondria, is, as we know, the powerhouses of the cells, and this is how we have been learning about that for decades, right? However, not until recently, relatively speaking, we've been very interested in mitochondrial function. And now what we see is, like, pretty much no matter which medical field you get into, and you talk to leading researchers in multiple medical fields, everybody's stumbling upon mitochondria, right, and mitochondrial function. Now, when it comes to cardiometabolic disease, there are two main events that happen when it comes to nutrition. One is the metabolization of carbohydrates and fats. So during postprandial conditions after a meal, about 80% of all carbohydrates are burned or metabolized in skeletal muscle, right? And it's time to really call skeletal muscle an organ. It's probably the largest organ in the body. And it's very important to see this, because within skeletal muscle, at rest, carbohydrates, which are turned into glucose in the blood, no matter what type of carbohydrate you have, whether it's good or bad carbohydrates, they're all going to become glucose in the blood, like fructose. Most of the fructose that you ingest is converted by the liver into glucose, right? So all that has to be metabolized, and under resting conditions, about 80% are done in skeletal muscle. And within skeletal muscle, this happens in mitochondria. So if you have a dysfunctional mitochondria or a mitochondrial that is impaired, you're going to have a metabolic challenge, because you're going to have to burn that glucose. And if you don't do it correctly, eventually you're going to have a problem, because that glucose is going to be building up in the blood, causing hyperglycemia, high blood glucose levels. And the pancreas reacts to that because it's dangerous to have high glucose levels. And the pancreas reacts by releasing insulin. And insulin triggers the transportation of glucose inside the cell. But it's not just about the transport of glucose inside the cell, which is what we've been hearing for decades, right? The world of type 2 diabetes has been evolved more at peripheral level, if you will, at the level of hyperglycemia, insulinemia or hyperinsulinemia, insulin resistance, even GLUT4, which are the transporters of glucose. They are stimulated by insulin, right? But we need to start talking about pyruvate and about the fate of glucose inside the cell, because this is absolutely key. Because one thing is to transport glucose inside the cell, and the other thing is to metabolize glucose to ATP and energy in mitochondria inside the cell, right? So this is the key aspect.
So there's two sort of critical things here we're talking about with regards to glucose and metabolic health. One is the ability to get glucose from circulation into the muscle cell. And you sort of alluded to the fact that that's been the story for a long time. And earlier you spoke about intramuscular fat. And so to my understanding, part of that story has been that as fat starts to accumulate in muscle tissue, it can make it harder to get glucose into the cell.
Yeah.
But what you're adding and saying is that the story of metabolic health and glucose metabolism and the difference between someone with poor metabolic health and an elite athlete goes beyond that. And we need to begin thinking about, once that glucose is within the cell, how it is being metabolized, which I believe from your work and is something that we're going to discuss, comes down to the function and health of the mitochondria.
Exactly. And then the problem is, like, if you don't metabolize that glucose inside the cell within mitochondria, then you have a metabolic challenge, right? And eventually, you're going to increase or you're going to elicit a condition of hyperglycemia, hyperinsulinemia, eventually insulin resistance. But the same thing happens also, or the same metabolic problem happens with fats, because fats can only be oxidized in mitochondria as well, right? So when fats cannot be oxidized in mitochondria, they build up, right? You cannot utilize them as energy, so you store them in adipose tissue, but you also store them adjacent to mitochondria in the muscle, right? And that eventually increases the reservoir or the deposits of fat inside muscle, right? Which is, again, as I said at the beginning, right, is highly related to insulin resistance, right? And that could be a connection between cardiovascular disease and type 2 diabetes. We know that about 80% of, not 80%, I don't want to say a percentage yet because we still have to learn more, but a big number of people with type 2 diabetes, they also have cardiovascular disease and vice versa. And this is what's been now termed more like a cardiometabolic disease, right? Because it's the combination of both diseases, right? So this is what probably a big nexus for this is, it happens in mitochondria.
Let's define the term metabolize. I know that term gets used a lot, and it's certainly sort of widely used within the literature talking about mitochondrial health and energy metabolism, but we may take it a little bit for granted, and perhaps someone's wondering, what does that actually mean to metabolize something?
Yeah, so it is to convert into energy, right? So the food that we have, right? We need to metabolize them to energy. So and we live in and that happens in mitochondria. So if you cannot metabolize it correctly to energy, you are going to pose a metabolic challenge to that cell, and because it's not going to be able to convert it to energy efficiently, so it either is going to be building up, right? And as in the case of fat, it's not good that it builds up around muscle. If it is in the case of glucose, it's an immediate metabolic challenge, because you cannot have high blood glucose levels because it can be dangerous, right? And another thing that happens too is that when glucose cannot be metabolized correctly inside mitochondria, pyruvate turns into lactate, and lactate is a key metabolite it's a signaling molecule. It's one of the most important signaling molecule. And this is the 52 years of work that my colleague and mentor George Brooks from Berkeley has been doing. Pretty much everything we know about lactate is because of him. And now the implications of lactate in health. So we know that lactate is a great signaling molecule that is probably very important for cellular homeostasis. But when it builds up and is too much lactate inside the cell, it become detrimental to the function of the cell. And we have seen that in different research that we and others have done. But that's the problem of not being able to metabolize nutrients efficiently. And this is happening already as a big part of Alzheimer's. Alzheimer's has been historically only been focusing on the beta-amyloid plaque, which is there, of course, and is highly related to the progression of the disease. But the whole thing is that every single drug against the amyloid plaque has failed. Now that has led to many researchers to try to look into different angles to understand Alzheimer's. And one of them is being insulin resistance and mitochondrial dysfunction in Alzheimer's, which is it's a hallmark. Before it was daring to even mention that, right? The connection between Alzheimer's and diabetes, or colic type 3 diabetes, but it's now widely recognized as a hallmark of diabetes, insulin resistance, and mitochondrial dysfunction. So there's a big problem for Alzheimer's patients to metabolize glucose as well.
I want to put a pin in lactate and come back to it once we've kind of walked through the different energy systems that the body is using and how this may change at sort of different exercise intensities. I know there's a whole sort of lactic acid story, and I've heard you before sort of clarify a few things. So I think it's important that we do come back to that. Another term I want to define here, Inigo, at the outset that is thrown out a lot is metabolic flexibility. What does metabolic flexibility actually mean?
Yeah, so the term metabolic flexibility, it's not a new term. We are starting to use it more, right? But it's a term that it was coined over 25 years ago by Kelly and Mandarino, as well as Good Pastor, and even before that, in the late 1700s, it was thanks to the work of Lavoisier, who started to look into aerobic metabolism, and so he started everything related to cellular respiration. But the term metabolic flexibility, in a very simple way, is the ability of humans to burn fat and carbohydrates and to switch back and forth. So when there is a carbohydrate availability, like elite athletes, for example, or fit individuals, they can use them very rapidly for energy purposes, and they metabolize it very rapidly. When there is not much carbohydrate availability, then you switch very well and very efficiently to utilize fatty acids for energy purposes. Or when you're fed fatty acids, you can metabolize them very well, right? And all that happens in mitochondria, or most of that happens in mitochondria. At rest, everything happens in mitochondria. During exercise, it can happen in the cytosol. So it's inside the cell, but not in mitochondria, right? Because you can use it through the aerobic glycolysis. But during rest, under resting conditions, everything happens in mitochondria. So that's, again, it's at the epicenter of metabolic flexibility. So people who are metabolically inflexible, there are people who cannot metabolize fatty acids or glucose properly, right? And therefore, as we mentioned earlier, it's going to pose a metabolic challenge because it can increase blood glucose levels on one hand, as also increase the fat deposits in the muscles as well as then in the adipose tissue.
And for us to kind of set the stage, I guess, to where we're going to go, I think, in this conversation, I mean, you mentioned there metabolic health and the importance of skeletal muscle. And I think for some people, that might be the first time that they've kind of really heard that or thought about that. And often, I guess, at a high level, you think more of muscle of, helping you do functional things, get up off the couch or lift a weight at the gym. So perhaps we just take a further step into the importance of having a good amount of skeletal muscle. What do we understand about the amount of muscle that we have, particularly as we age, and how that does intersect with our metabolic health?
Yeah, so muscle makes up, depending on your body composition, or 50% of your body, 50% of your protein. And as we age, as we get beyond 40, the efficiency of how the body maintains it tends to start downward. Muscle is a major source of glucose metabolism. It's a major source of fatty acid metabolism. And if you have problems with blood sugar, with blood lipids, chances are your muscles aren't healthy. So we talk about them from dietary standpoint or heart standpoint or all kinds of things, at body fat, adipose standpoint. But the reality is muscle is really where it all begins. And unless you're super physically active, that is on a downward trend as we get older. So, how do you manage that? What can we do about it? Those are all topics I think are really interesting, and I think we can do things to make it better.
When we say, a good amount of muscle, and if you were to kind of think about as we age, often you hear people saying, do resistance training. It's important to maintain a good amount of muscle. And I'm kind of assuming that there's a bit of a spectrum where you go from sort of under-muscled, where maybe you are putting yourself at risk of some of these negative metabolic consequences, to having sufficient muscle. Is that something that we've been able to quantify within the research? What is a good amount of muscle? If someone's listening and thinking, well, I'd love to know if we know that firstly, and then if I can test it.
Yeah. I don't think there is any really good number. We typically think of it from the other direction. We think about what's an unhealthy amount of fat. Well, we think that, if you've got more than 30% body fat, then you're likely going to be at health risk. So, that means the rest of it's lean body mass. What percentage of that is muscle? I don't have a real number to give you on something like that. I think that you really look, and again, somebody who's 6'6" is going to have a different level of muscle than somebody who's 5 foot, and they both can be perfectly healthy. So, the issue is, how functional is it? What are you doing? Are you physically moving? Are you physically active? Is it metabolically healthy? And you can be, both the activity and the nutrition are hand in hand in terms of how healthy it is. So I don't think the amount is the key. For any individual, for you or me, we could simply say, well, for me, X amount of muscle is probably a good healthy level, but that's probably quite different than what it would be for you.
Is this where strength comes in? Is strength a kind of better proxy for sort of determining our risk of, say, frailty or even total mortality? I often see grip strength used in the literature quite a bit.
Certainly mobility in the aging literature, which functional aging is not exactly my specialty, but walking, gait speed and ability to get up out of a chair, and some of those are very much predictors of health and mortality. So strength is certainly part of it. I also think a lot about the metabolic aspect, which someone can be fairly metabolically healthy and not necessarily be super strong. You know,
Mhm.
I don't personally think that resistance exercise is the key to metabolic health. You know, sort of the flip side of your question. So
Mhm.
I personally think people need to practice some level of both resistance, HIIT type of exercise, some level of resistance and some level of aerobic, because they're not the same outcomes.
And when you mention metabolic health, translate that for someone listening. Like, what in terms of actually measuring something? Are you talking like HbA1c or fasting blood glucose? What are we talking about when we mean metabolic health?
Yeah, so I focus a lot on protein turnover. So having good rates of protein synthesis, responding correctly, I think that's important. I think blood glucose, blood lipids are also important. Your mitochondrial health determines your ability to oxidize blood lipids.
Hmm.
Those are the kinds of things I think about with metabolic health.
Hmm.
Um, do you have the right level of branched chain amino acids? Are you metabolizing your lipids? Are your triglycerides in your blood at the right level? All of those things are part of that package.
So would you say the goal here, from your view, the goal here is to have a sufficient amount of muscle, whatever that is for the individual, to act as a good way to kind of dispose of blood glucose, to metabolize glucose, and at the same time, healthy functioning mitochondria, and trying to avoid that sort of visceral fat buildup around the organs. Is that a kind of decent summary of metabolic health?
Yeah, again, the amount, it's about activity.
Mm.
Um, the the larger your muscles are, if I started lifting more weights, I would convert muscles toward white muscle type. I would have less mitochondria per unit of muscle. So
Mhm.
that doesn't necessarily make it better for metabolizing glucose. I approach it quite differently. I think about, what's my calorie need? What's my carbohydrate threshold? So there's a minimum need of carbohydrates of around 130 grams per day. We could debate that number.
Mhm.
But then I think about you can add about 60 grams per hour of intense exercise. The question is, how do you balance all of those things? And that relates to your muscle mitochondria. So are you doing aerobic activity? The strength aspect sort of are you strong enough to do those activities functionally? But the size of the muscle doesn't necessarily lead to metabolic health.
Mhm.
Um, if you want to think about animal research a little bit, there's classic things in like the swine industry where if you over muscle an animal, it becomes metabolically incredibly unhealthy.
Mhm.
Uh, they're very prone to lactate toxicity and things like that. So, big muscles isn't the answer. Healthy muscles is more of a mitochondrial and functional mobility as opposed to just big.
Okay, quick ad break to introduce you to one of our very important partners, 38 Terra, who helps make these videos available to you at no cost. You really must try 38 Terra's DMN prebiotic, the science-based daily multivitamin for your gut microbes. A simple and delicious way to take your gut health to the next level. Once you start, there really is no going back. I have it every morning. Get 10% off your DMN at 38terra.com using the code THEPROOF. That's 38terra.com and use the coupon code THEPROOF for 10% off. Zone 2, Inigo. Let's define it. I know we probably have earlier in the conversation, but simple definition. What does Zone 2 actually mean?
So again, there are probably different definitions. Some of them are closer, other ones are a little bit more separate. I just have my own definition, right? That I've been using for 30 years, and for me that's the exercise intensity where someone can improve mitochondrial function the most. Not the only one, not the only zone, because other zones are going to always be beneficial. Any zone will be beneficial. But from what I've seen is looking at fat oxidation in the laboratory and lactate clearance capacity as mitochondrial surrogates and as mitochondrial substrates and therefore surrogates for function. That's what I see. That's how I cannot define in a nutshell zone 2.
I think many of the listeners will be thinking, how do I know that I'm in zone 2? And there are a lot of different calculations online. There are running tests, there are lab tests, etc. How do you encourage people to think about this?
Yeah, that's a great point. So I think that as we're starting to look at exercise prescription for the mass market and for many people, as opposed to just to elite athletes, right? We're going to see more and more exercise physiology or metabolic laboratories around the world, right? And in fact, it's happening, right? Until recently, there were very few laboratories around the world who did this test to specifically find out your training intensities, right, based on heart rate or power output, right? And they were only for the elite athletes, right? And then now more and more are popping up around the world. And people are not so scared to go to a laboratory, because I remember when I started doing this in the US for health purposes with patients 15 years ago, people were scared because they say, "Oh, I'm not an elite athlete," right? Or they would see a cycling jersey of a runner's jersey on the wall and say, "Hey, I'm not one of those," right? No, but this is not about that, right? This is about you. And so, anyways, that those laboratories and those testing, they're becoming more sophisticated. And people running those tests, they're all more and more professionals. Before, there are not that many professionals working in this area, and people would go to their local university, and with all the respects to graduate and undergrad students, they were seen and tested by them, right? Now you see a lot of professionals who they were undergrad or graduate students and become into this field, right? So that's on one hand, but there are people out there that they cannot find a place, right? There's not a laboratory in their town, or maybe it's too expensive and they cannot afford it, right? So for those, and from my experience, right, I think that the breathing and talk test, it's a great way, and I'll explain it. So, like when you and I talk like this now, when you can maintain a conversation like this, you're in your zone 1. You're recovering. You're not stimulating much, right? Zone 2, it would be like a hard conversation to maintain, right? If you imagine yourself exercising with someone else, you could maintain a conversation, but it will be costly, right? You will be talking with some difficulty, but you could maintain it, right? Not for a long time, not for 1 hour, because it would be too fastidious, right? But you could maintain it. That would be kind of what we see the results in the laboratory, and it kind of corresponds to that, right? And then zone 3 would be an exercise intensity where it's very difficult to maintain a conversation. Very difficult. Just exchange a few phrases or a few words, right? Then zone 4, no conversation. That's it. Maybe one word you can say. And then zone 5 and zone 6, yeah, there's no possibility, right? But I think that, and I honestly, and I know it might sound old school, but we have now watches and all these algorithms, that gives us zones. The immense majority are far away from giving you the right intensities, because those algorithms are not individualized yet. It'll happen at some point, right? But at this point, I really think that the talk and test is much more accurate than the immense algorithms that you find out there in all these brands telling you the training zones. So, and it's easy to do. And again, from my experience and the data, the hardcore data from laboratory, it's not that matches perfectly, but it corresponds quite well.
Yeah, and I think, it's just worth us remembering that there are so many people living a sedentary lifestyle. So trying to remove barriers to just get people moving is a great thing. And what you've just described there is really accessible to people. Are you a little bit puffy? Perhaps you have a little bit of sweat happening, but you can carry that conversation. If you were on the phone to someone, they would know you're exercising, but they could still have a bit of a conversation with you without it being sort of too interruptive.
And the good thing with that too is that as you get fitter, you can be displacing that intensity, right? So now maybe someone is sedentary and obese or overweight, and maybe just walking around the block, right, might be tiring, right? But that might be the zone 2, for example. But maybe in 1 year, that person can do like a brisk walk, right, and be at that same intensity, right? So that's what you can guide yourself through this simple test, right? Which at the same time, this zone 2 intensity it's something that's sustainable for life, and again, I also say that any intensity will help, and you need, as we discussed, higher intensity to maintain your fitness and your glycolytic capacity. And obviously we haven't talked about resistance exercise, which is very important, right? And more than I do, but the thing is, like, yeah, just when it comes to both exercise and diets, I always ask people who do these extremes exercise routines and extreme diets, and they have great results. The immense majority are just temporary, because the immense majority go back to where they were. And when you ask them, can you do this for the rest of your life? The answer is no. So if you cannot do a diet or an exercise for the rest of your life, it's not going to work. So you need to have some sustainability, both in your nutrition and both in your exercise. And when it comes to exercise, a zone 2 is something that anybody can do for the rest of their lives.
You mentioned some of those algorithms, and I think the most crude sort of calculations that are out there are using max heart rate, 220 minus age, and then kind of just multiplying that out by the various intensities of the different zones. And perhaps a step better, there's calculations like the Carvenin formula, which I'm sure you're familiar with, that uses heart rate reserve. If someone is going to go out and use a calculation out there, is the Carvenin sort of formula, or a formula that's using heart rate reserve, better than one that just uses max heart rate?
Probably, but still, the thing is, and this is what I've also learned working with athletes and also regular people, is that the heart rate response to exercise is so individual. You can have someone with the same age, and one's maximum heart rate might be 180, and the one might be 200, right? Or 160 and 200, right? So, and regarding the cardiac reserve, that could vary significantly also among individuals. So I think it's probably more accurate, right? But I don't think we're not there yet, looking into these algorithms when it comes to heart rate, because it varies a lot. And I think that, again, it's one of the things, it doesn't represent necessarily what happens at the cellular level. I think that the future is going to come in the biosensors, where we're going to be, we're working with one company, with one biosensor already, that we think is going to be a big deal at some point. But the biosensors that they're, kind of, people have now some glucose, that if you're type 1 diabetes, it's a game changer. If you're not, it's cool to see how your glucose goes up and down. Eventually, it's physiology and metabolism 101. And eventually, it's just you can get some education, but eventually you will not using it much, because you're not type 1. But the more sophisticated biosensors are coming with more metabolites that come directly from your cells, and that's where you're going to be guiding exercise in a much specific way.
What do you think about the devices? I sent you a few on email that you breathe into, that sort of supposedly tell you what type of fuel you're using to produce ATP.
Yes. So those are very good. That's a very good question out there, and without a doubt, it's a starting of a movement of trying to understand better how your metabolism works, right? But one of the things is that they need to be very well calibrated. And this is my problem that I have, right? And this is my experience from 30 years working with all these metabolic cards. So we use in the laboratory metabolic cards who are like $30,000 worth, very expensive, very delicate, and those are the state of the art. And they really need to be very calibrated. So they have CO2 sensors and oxygen sensors as well. So and they, believe me, they get decalibrated all the time. They're very sensitive. So, and if they're not correctly calibrated or they get decalibrated, they're going to give you false readings, which happens all the time. And in fact, there's a brand, I don't want to name any brands, but there's a brand that I've been using to do my research and to get these calculations all these years, which to me is the best out there, is the most accurate. And you can see the accuracy very well. But the problem is that it's not as fancy or has these graphs or hasn't evolved in 30 years as other brands, right? Other brands, they have these nice and fancy graphs, but maybe they're not as accurate as this other brand, right? But anyways, but we're still talking about equipment that are $30,000 worth, right? But these devices are like 200, 300, 400. Sure, so some of them, they have CO2 sensors, right? And O2 sensors. But how do you know first that how do you calibrate them, right? And therefore, how do you know that the readings are right? And second, how do you know when they stop functioning? And because we know from these very expensive cards that you need to replace the sensors often, sometimes every year, sometimes every 2 years, 3 years, right? And that's the thing, like I see that the concentration to calibrate them, you need to really put oxygen and CO2. And the way they do this, when you do the calibration from ambient air, right, the metabolic card gets oxygen, and it has to read 20.94, which is the oxygen concentration. And then CO2 is usually the one that is the most problematic. It has to read 0.03%, right? So when you calibrate those manually or automatically, multiple times, you see that the CO2 concentration is 0.05 or 0.06 or 0.01. And the card, the metabolic card, allows you to proceed with the test, right? So without a doubt, you're going to have false readings. And again, we're talking about a $30,000 very sophisticated piece of equipment. Now, how do I know in these small devices that the reading that I have is the actual one, right? So that's, and again, I'm not criticizing necessarily, right, those devices, because I think that they can give you like a trends and where you are, and if you're burning more fat or less. But I think that, yes, I don't know if I don't know the calibration, the precise calibration. I don't trust it much, and then you go to some of the websites of, not all, but some of these devices. And when you go to a website, you see hack your metabolism or own your metabolism, or the most advanced metabolic machine ever. Like, it's a red flag, right? Because there's not such thing, right? Now you see rings, right? That they go to their website and you go, oh, the most sophisticated piece of metabolic measurement you can have. It's like, come on, it's a ring, for Pete's sakes.
That reminds me of the way kind of zone 2 or training at max fat oxidation is often conflated with this magical fat burning zone and fat loss or body fat loss. Is that something that you could clarify for the listeners?
Yes, and the thing too is, like, when we talk about this, that's an excellent question too, and I address, because when we talk about fat max and fat oxidation, we're talking about very, very, very small amounts of fat that someone oxidizes. So we're talking about, like, for example, if you're an okay fit individual, your fat max is going to be 0.4 grams per minute, around that, amount. If you're a world-class athlete, we're talking about 0.8. If you're a moderately healthy individual, your fat max is going to be about 0.3 grams per minute. So you just do the math, right? If you are exercising 60 minutes at your fat max, and let's say you're 0.35, you're actually losing 21 grams of fat. That's it, right? In 1 hour, right? So there's no magic like, oh, wow, yeah, I just burned so much fat today. No, it's not such a thing like that. You burn a little bit, but a little bit every day, right? If you then also match this with proper nutrition, right, and stay at some caloric deficit, then yeah, those 21 grams of fat, right, times if you do this 5 days a week, right, times 4 weeks per month, yeah, that's half a kilo, right? So that's half a kilo. It's not bad. You put that in 12 months, and that's 6 kilos that you lose, right? And that's exercising 1 hour. If you exercise an hour and a half, we're talking about 9 kilos, which could be incredibly beneficial for your health, right? So this is what I think, that there's no magic bullet that, oh, wow, your fat max. People sometimes think, oh, I'm losing so much fat, therefore I can have a burger, a cheesy, greasy burger because I exercise, And that's the other thing too of many of these machines or even watches or so, like, you burn 700 calories today. Yeah, but they're not telling you the partitioning, right? You could have burned 100% of those 700 calories derived from carbohydrates and 0 from fat, because your exercise mode or dosage was not the right one, right? Or you might have a 50-50 or 70-30. So that's going to obviously impact, right, how much progress you make when it comes to lose weight. And this is one of the reasons why a lot of people who exercise regularly, they cannot lose weight. And because they say, man, I'm burning 700 calories or 1,000 calories every time I exercise, and I can't lose weight. Well, first, you're probably overeating for how much you burn. And second, you're not burning much fat, if that at all, when you exercise. So this is why it's a tricky concept, and it's about patience also.
Doesn't it just come back to energy balance at the end of the day? So in your workout, if you burn or expend 400 calories from mostly fat versus someone else who works out for a shorter duration but also expends 400 calories mostly from glucose, isn't the net effect on their body weight going to be the same despite the difference in substrates being used to produce energy?
I don't think necessarily. That's my opinion. That there's there's energy balance is very important for sure, but it's also an energy efficiency and the type of substrate. So if you want to lose fat, you want to burn more fat than glucose, because that comes from adipose tissue, right? The thing is that we're used to also seeing a lot of people doing high intensity exercise and who are already very fit to start with, right? So they have a good, probably because they haven't achieved a mitochondrial decay, because since they were kids, they've been fit and doing exercise and moving a lot, right? You see these people doing these high intensity exercises, and they're very fit, and they don't have much fat. That's maybe the calorie balance is more important for them. But maybe for people who are overweight or obese, the energy balance should be more towards burning more fat and restricting also calories from your diet to achieve that calorie balance, as well as to improve mitochondrial efficiency through specific targeting of training intensities.
I guess I'd always just looked at the kind of the dietary intervention trials looking at low carb diets that are high in fat versus high carb diets low in fat, and at least at the 12-month mark, and some of this could be adherence, there doesn't seem to be a big difference in body fat. And the way that I've reconciled that is that the people on the high fat diet, although they're burning more fat or oxidizing more fat, it's dietary fat, not necessarily stored body fat. But that's interesting for me to kind of think about further. Coming back to zone 2, so you've got the talk test, being a little bit puffy, a little bit sweaty. We spoke about those different formulas that are out there, and it sounds like that if someone is using any of those algorithms or formulas, they're still going to want to come back to the talk test and pair the two together. I recently did a VO2 max test in a lab, and through that VO2 max test, they calculated my zones. I know that's different to lactate testing per se. I noted that there's an upper and a lower bound. So for me, zone 2 came out at 129 to 142 beats per minute. Let's just pretend that that is my accurate zone 2. And you might say that we need to do lactate testing to get very accurate. But my question to you is, when I am going out and doing zone 2 training sessions, does it matter where I'm sitting in that range? Do I need to get right up to 142 beats per minute at the upper sort of bound in order to get the stimulus that we need to drive these adaptations?
Yeah, that's a great question too, and it's good that you have like relatively like a small range, right? I've seen people getting a range of 30 beats per minute, for zone 2, and I guarantee you that there's not such a big range. We usually, the range is somewhere between 5 and 10 beats per minute, right? At least with my calculations and how they work for me. But yeah, absolutely. I think that you want to go more towards in the middle, right? To be more conservative towards the high end of zone 2. That's when you're going to push those bioenergetics the most, right? And driving into fat max before you start engaging more the fast twitch muscle fibers and switching more towards increasing glucose as energy fuel. But you need to be very sure that the zone 2 is that zone 2 if you go in the high end. Otherwise, I would stay more in the middle.
So if we are dipping in and out of zone 2, does that make that training session somewhat redundant or diminish the sort of returns that you're going to get? So if you're doing, say, 60 minutes on a stationary bike, but 45 minutes of that was zone 2, sporadically throughout that session, you were dipping down back to zone 1, and then at some points you were going into zone 3. And this is something that I think people who go out and do rucking or hiking face because they're going up and down hills. Is that a problem? If we're doing zone 2 training, do we really need to get into zone 2 and then stay in that zone?
That's a great question too. And I think that, and this is my humble opinion, I think that it comes to the timing that you spend at your zone 2. And like, as you say, some people who are doing sporadically zone 1, zone 3, zone 2, if they're only doing this for 45 minutes, maybe the actual portion of zone 2 might be 30 minutes. And what I have seen is that, and it's one of the 3 pillars that I see, is one, to identify the training zones, the intensity, right? Second is the frequency, how many days you do this. And the third one is the duration, right, of each session, right? So I see great results with people when they reach around 1 hour, right? So like if you do 1 hour purely as zone 2, you're going to get good benefits. But if you go a little bit above and below, or even to zone 4 here and there, you might want to have a longer session, which is 1.5 hours, for example. Whereas those 30 minutes is like when you oscillate, but the pure zone 2 is in that 1 hour, right? So that's where you have the stimulation within one session. That's kind of how I see it. And it also depends on your form and your peak. Let's say that you do like a high intensity interval in the middle of the session and you only do 1 hour. So if you do a high intensity interval, you're going to have a lot of lactate, and it's going to be there for about 15 minutes. And as we saw, lactate is going to inhibit lipolysis. It's going to inhibit transportation. So you might lose about 10, 15 minutes of the session, which again, if you do an hour and a half, it's no big deal. Like I do that, when I go on the bike, I do usually an hour and a half, an hour and 45 minutes. So I don't have much time, but that's enough for me. But yeah, here and there, I do glycolytic intervals because I love to do them, and they're good. And now with applications like Strava, you want to see where you fit in with the rest, and they're dangerous. But anyways, I see that. I love this, this side of trying to compete with yourself, right? But yeah, I do this for maybe 7-10 minutes, like a zone 4 interval, and then I'm in a relatively good form in 10 minutes. I'm going to go back to normal levels. So yeah, I sacrifice 15 minutes out of my an hour and 40 minutes. So I'm good. I'm still doing an hour and 20 minutes or so at zone 2, right? So, but yeah, I think it's about duration at zone 2 that you can afford.
And ideally within a session that is consecutive minutes in zone 2.
Yeah, yes, that's the thing. Yeah, and like if people do a lot of intervals in zone 2 and intervals in zone 2 and intervals, it's not going to be your zone 2. You're going to be recovering from the interval, right? And you're going to be still going through a lot of glucose, right? So I think that again, like I like to have it more towards the end of the session. Or if you have like a good hour and a half, hour and 40 minutes, you can have one interval in the middle of the session or 2 hours. And if you can allow, and if you're moderately fit, in 10 minutes on the downhill or so, you can come down to like a zone 2, right? But if you're not very fit and you want to do several intervals, you're going to be up there. It's going to be taking time to come back to zone 2. So in that case, you might want to do an interval towards the end.
What is the twin cycle hypothesis?
The twin cycle hypothesis was my attempt to put together all the observations on how the body actually worked, how the body dealt with food and metabolism, and what went wrong in type 2 diabetes. So over the years, we'd learned, firstly, that muscle was very resistant to insulin, and using MRI techniques, advanced MRI techniques, we could measure the glycogen in muscle. And, in fact, use this to show that people who had normal insulin sensitivity in muscle stored a lot of their food as muscle glycogen within the first 5 hours after eating, 1/3, really quite a lot. Whereas people who had low sensitivity to insulin in muscle, so-called insulin resistance, those people stored almost none. And from other work, we knew that the only way that glucose would be handled, it's not being stored properly, the only way it could be handled would be for the body to turn it into fat. Now that sounds like magic, but that's exactly what the liver does. And so that excess glucose will be shunted into fat, and people will be more likely to build up fat in the liver. Now, we'd shown fat in the liver causes the liver not to respond to insulin. Now, I put all this together, and the twin cycle hypothesis runs like this. Basically, a little too much food over a long period of time will cause fat to start building up in the liver. And when the liver starts getting resistant to insulin, it will start putting out too much glucose, because insulin usually dampens down the constant production of the liver. of glucose. So there we have glucose rising a bit, but what happens next is that the pancreas kicks in and insulin levels rise a bit to just bring things under control. Now that's fine temporarily, but unfortunately insulin speeds up the process of turning glucose into fat. And so we've got a vicious cycle that started running. That will run on, and glucose levels will gradually peg up. But it's not just the glucose that the liver puts out. The liver also puts out fat for the rest of the body. The liver really supplies you with the energy you need to live every day. Overnight, it's the glucose coming out from the body that keeps your brain alive, and the fat coming out from your liver that keeps the rest of the body alive. That's what they use to burn for energy, second by second. It's an astonishing process. But if there's too much fat in the liver, then that one liver cycle will have a knock-on effect because it will leave too much fat in the blood. The liver puts out too much fat. It will be delivered to all tissues. Now, any excess fat would usually be stored under the skin, and metabolically that's safe. It doesn't cause any metabolic damage. However, in the situation of excess and with a relatively full subcutaneous under the skin compartment, then fat's going to build up elsewhere, and that's the problem. And it's when fat starts building up inside the pancreas that really the action starts. So we have a second vicious cycle in the pancreas. The fat stops the insulin-producing cells from working properly. Lo and behold, that means glucose levels are higher after every meal. And lo and behold, that means more glucose is going to be turned into fat. And so we have these twin vicious cycles interacting. The importance of this twin cycle, Simon, was that it explained type 2 diabetes as a simple chain of events. Yes, interacting cycles, but a single cause. Now, that is simple. And what we see in populations is when they're overfed, diabetes erupts. If they're relatively starved, diabetes goes away. So all of a sudden, we had a handle on this, and it was a complete revelation and a move away from what all the experts were saying up to 2011, that type 2 diabetes was a complex heterogeneous disorder caused by multiple different factors. Well, that's nonsense. Basically, you inherit your genes, but if you put on a bit too much weight, heavier than you can bear, then these twin vicious cycles will start turning. And being a hypothesis, it could be tested and shown to be right or wrong.
You said there that the twin cycle hypothesis provides an explanation for a single cause. What if someone is thinking, well, hang on, how can excessive calories explain this if not everyone who becomes overweight or obese ends up with type 2 diabetes?
That's a very good question. The first point to make is that there's a wide range of thresholds at which people will develop type 2 diabetes. So in our most recent study, we've demonstrated that those slim people who get type 2 diabetes have got too much fat inside their organs. They simply don't show the fat. So there's this matter of how much fat and this personal threshold for fat. But there's a further point which is really important. About 70% of people of white European ethnicity will never get diabetes, no matter how much they eat, how fat they become. And in fact, at the moment, 73% of people with who have a body mass index over 40 do not have type 2 diabetes and show no signs of getting it in the near future. So we can see that it's only a proportion of people who are susceptible. And that is the stop-go of getting type 2 diabetes. So there are really two stages. One is the eating too much. The other is the genetic factor. But why do I say that it's just one? Well, it's because I'm talking to a group of individuals. They are one person each. And in my consultations with patients, I only have one person in front of me. And that person comes in with a ready-made collection of genes. They are themselves. Now, doctors have to practice the art of the possible. So I'm dealing with individuals. If a person presents to me with type 2 diabetes, they have insulin-producing cells that are susceptible to fat. And that is the whole point. So this disease is simple to understand.
Right, so it's not necessarily fat or being overweight or obesity that is the single explanation, but it is fat getting inside these organs, the liver and the pancreas specifically. Fat, I guess, where we could say it shouldn't be in individuals that are more susceptible to this. So certain individuals, as they're gaining weight, are more genetically predisposed to having fat stored within organs, whereas other individuals have a greater capacity, would that be the right terminology, to store more fat subcutaneously and not inside these organs?
Yes, that's absolutely right.
Okay, so let me throw back to you what I grasped from your explanation of the twin cycle hypothesis. So it all kind of begins with this positive calorie balance. So a very small calorie surplus over a long period of time, coupled with muscle insulin resistance. This results in an increase in blood glucose, or that extra glucose. The body has to do something with it. Instead of forming glycogen in muscle tissue, you get an increase in de novo lipogenesis, which is the conversion of glucose to fat within the liver. With the increase in liver fat, you get insulin resistance in the liver. Insulin's job at the liver being to slow down or halt the flux of glucose from the liver into circulation. So with that, you get an increase in blood glucose. The response from the pancreas there is to increase insulin, so insulin levels go up, and insulin then increases or drives more fat production in the liver. Eventually, the body has to do something with that excess fat being produced in the liver, packages it up in lipoproteins, these VLDL, very low density lipoproteins, which are an ApoB containing lipoprotein and are therefore atherogenic, and they go out into circulation. If the subcutaneous fat storage has been exceeded, that excess fat that is now in circulation, it has to go somewhere. And eventually it can begin to build up in organs, particularly the pancreas, which then can begin to affect the beta cells in the pancreas that produce insulin, such that there is reduced insulin in response to ingesting a carbohydrate-containing meal. And with that, you get increase in plasma glucose, and the liver begins to convert more glucose into fat, and so forth. The cycle kind of self-perpetuates. Did I grasp all of that correctly?
Yes, that's absolutely correct.
Just to kind of double click on your concept, the personal fat threshold, I guess a phrase that I believe that you coined that. The personal fat threshold speaks to how much fat you can store subcutaneously. Is that right?
Yes, that is the essence of it. Although there is also a liver component. So some people can be very large and obviously have fat under the skin, excess fat under the skin, but be metabolically normal. Relatively small percentage, but this is entirely recognized. At the other end of the scale, there are some severe genetic conditions with absence of subcutaneous fat. And guess what? They have high levels of liver fat, high levels of fat delivered to the pancreas, and a proportion of people get type 2 diabetes. Now, a very high proportion compared to other thin people, but even so, it's not 100% because some people have the problem with storing fat and the good kind of beta cell that doesn't bother about fat being on their doorstep. So, yes, the personal fat threshold is largely a matter of being able to hold fat in the tissues under the skin and remain metabolically safe. If you exceed your personal fat threshold, you're likely to have diabetes if you're susceptible to it. And so in our recent study, the Retune study, we found that getting people in the normal or near normal body mass index range to lose an average of 6.5% of their body weight, they became non-diabetic. 70% became non-diabetic. So we need to set in context this unfortunate idea that doctors and nurses tend to cling to, that if you have a normal body mass index, you mustn't lose weight. Well, that's absurd, because the concept of normal is rooted in a population, and the advice is being given to one person in the consultation. We're all individuals, and I know from my patients that everyone likes being treated as an individual.
That person there, which I think is about 1 out of 6 people with type 2 diabetes, is that right, who have normal BMI, what you're saying is that despite the normal BMI and from the outside, looking at this person, you may believe that they don't have any weight to lose. That person has exceeded their individual personal fat threshold and has excessive fat in the liver and pancreas to the point where things like fasting blood glucose and their HbA1c are putting them into pre-diabetes or type 2 diabetes kind of territory.
That's correct.
Okay, and the Retune study that you just did recently, that you just mentioned there, that was, if I have got this right, that was the intent there was to see if type 2 diabetes in people of normal BMI shared the same etiology, the same kind of cause as type 2 diabetes in people that were overweight or obese. So within this study, you were able to actually measure that with the reduction of fat in the liver and in the pancreas in these people that have a normal BMI, with that insulin resistance reduced and blood glucose normalized?
That's absolutely correct. All the processes that we had shown underlay diabetes in people who were overweight or obese were exactly the same in people who had normal weight. Now, we were able to chase the fat and show that liver fat was high. The VLDL triglyceride that we've mentioned before, that's high. So the minute by minute, second by second delivery of fat to the insulin producing cell, the level of fat in the pancreas is just a marker for that. But that delivery of fat continues, and the relief of that when people lose weight is associated with a recovery of ability to make insulin. So yes, the Retune study looked under the bonnet and saw the mechanisms of diabetes are exactly the same in these slim people as in heavier people, again underlying the fact that type 2 diabetes is a condition of homogeneous etiology, although in heterogeneous individuals.
So if someone's listening and they're thinking, gosh, I'm in the normal BMI category, I'd love to know if I have exceeded my personal fat threshold, would I be right in assuming a basic blood test that includes triglycerides and fasting blood glucose and perhaps ApoB or non-HDL, that those sorts of markers along with
waist circumference are going to be a window into whether you've exceeded your personal fat threshold or not?
I can't say that we can be absolutely sure on the basis of measurements. I can give a few guides. Yes, a person who's exceeded their personal fat threshold is likely to have a moderately raised insulin level. They're likely to have a moderately raised fat level, triglyceride level. And also, they're likely to have gained weight in adult life. So many people regard themselves as being normal weight, but they're comparing themselves with their friends of similar age, all of whom have put on weight. And when we ask the critical question, can you wear the same trouser waistband as you wore when you were 21? Then people get it. They can't fit into the size, say, 32-inch trousers they wore at the age of 21. They're now 35, and they think that's okay. Well, it might be okay for most people, but it might not be for them. So you see, it's a matter of likelihood, and all I can say is that the personal fat threshold can only be defined exactly if a person has type 2 diabetes, loses weight, and discovers for themselves where that threshold lies. For some people, and we know this from our biggest study, the direct study, some people need to lose all 15 kilograms. In fact, one person needed to go on to 20 kilograms to get rid of the fat sufficient to get rid of their excess above the personal threshold. But some people only needed to lose a small amount. The majority needed to lose at least 10 kilograms. So you see, that's how the personal fat threshold works. At the moment, despite my best efforts, we've tried to develop ways of measuring it. I can't offer any concrete way of knowing for certain. There's only a matter of degrees of risk at the present time.
And you said there the only way of knowing is to lose weight. And I'm assuming to there you're mainly keeping an eye on blood glucose. And I say this with the definition of remission, I guess, in mind here. You'd be looking at blood glucose returning to the normal range without any type of blood glucose lowering medications. Is that how you would know that you are below the personal fat threshold?
Yes, that's the final arbiter. And also we would expect the level of triglyceride to have fallen by 30%. It's 50% raised at baseline, coming down to normal is a fall of 30%.
And coming back to the direct trial, which you mentioned before, which I guess is one of the more prominent trials of yours that's tested the twin cycle hypothesis. It was 15 kilograms, I think you mentioned, that seemed to be an important kind of number, 15 kilograms of weight loss. So that was the typical weight loss that was required for people within that study to get enough fat out of the liver and pancreas to enter remission?
The average weight loss immediately after the low-calorie phase, which in direct was a 12-week phase, the average weight loss was just over 15 kilograms. So, yes, that was an average. But some people needed all of that 15 kilogram weight loss to get rid of their diabetes, because putting on even a small amount of weight allowed the diabetes to come back when we tested subsequently. Other people could manage to put on quite a bit and still be free of the diabetes, so that at 2 years down the line, because DIRECT was a 2-year randomized control trial, 2 years down the line, in the weight loss group, the average weight loss had dropped to 8.8 kilograms. And even so, 1/3 of the entire group was still in remission from the diabetes. So you see, that's how it works. we need to aim for the 15 kilograms weight loss. That will take most people into the range where the chances are they'll be free of diabetes. That has the important effect of demonstrating to everyone concerned the possibilities. So if at, say, 15 kilograms a person is in remission, but then life kicks in and they're distracted with other problems and the weight increases by, say, 3 kilograms, they're going into 12 kilograms. If they're still free of diabetes, well, life goes on, but the chances are that they will just continue to put on a bit of weight, especially if they've discovered they can put on weight without getting their diabetes back. Suddenly, say at 10.5 kilograms, the doctor says, well, I'm sorry, you've got your diabetes back again. What do you want to do about it? Are you going to lose more weight again? Or I can give you these drugs? Well, you see, the target of 15 kilograms is fairly secure and a good target for most people. And it's also a wake-up call along the lines of get real. You know, how much extra fat do you think you're carrying around? Because most people in our studies have put on more than 15 kilograms than they were when they were in early adult life. So 15 kilograms is not a complete return to a state of youth. It's a return most of the way and will be sufficient to achieve the metabolic goal.
So in indirect, you mentioned there was a 12-week low-calorie dietary intervention. Average weight loss was 15 kilograms. So was that average weight loss, Roy, from the 12-week low-calorie intervention? And perhaps you can explain to someone what that kind of looked like if they haven't heard that being explained before. Or was that 15 kilograms achieved through the 2 years by doing this sort of low-calorie cycle multiple times?
No, and this is one of the really important points of our work, that to lose weight, it's much easier to do it in a short, distinct period of time. You've got a short, focused period of time. You can plan when to start it, avoiding birthdays and wedding anniversaries maybe, and you know that, okay, you're going to have to give up certain things, perhaps avoid some parties during that time. So the defined nature of this low-calorie period is quite important. Also, the original reason why I designed this approach to weight loss, to test the counterpoint, in the counterpoint study, this twin cycle hypothesis, the original reason was that the old literature pointed out that what they called very low-calorie diets, and they were very low, were not associated with hunger. Now, that was a fascinating detail that has stuck in my mind from the old literature, and so that was one of the reasons I went for it. And indeed, we find that people are very hungry over the first 36 hours, but you just got to tough it out. If you feel too hungry, drink a pint of water. Have a list of things in advance to do, fixing that door on the cupboard, or going out and sorting out whatever in the garden. So that first 36 hours is difficult, but after that, people suddenly find that they're not hungry all the time, despite only taking this diet, which in direct was 4 200-calorie liquid shakes. That's a packet of powder made up in a pint of water. Partly because it's high protein, about 25% protein, it's actually quite satisfying, and it does actually fill you up. That's the recipe for restricting yourself to 800 kilocalories, just 200 per meal. As I say, in direct, we used 4 sachets a day. In our early studies in Newcastle and continuing now, we use what we believe is a better accepted version, which is just 3 shakes a day, but a large plateful of salad foods or non-starchy vegetables. That allows people to enjoy feeling crunch. It eases the matter of this second phase, which is moving from the low-calorie diet back towards normal eating. How do we do that? After Counterpoint, I was surprised when people came to me and said, look, Doc, it was actually much easier than I expected going on this low-calorie diet, but it was so difficult coming off it. So we had to design a stepped food reintroduction. So in Counterbalance, we introduced one meal and just kept on 2 shakes per day, and then we introduced a second meal a week later and carried on with 1 shake a day, and then finally, after a further couple of weeks, we dropped that final shake. So people gradually got used to how much of normal food to eat, what to eat, and having a blank slate upon which to write new dietary habits is really rather good. And so we can re-educate people, and all of them are primed in advance that when they get back to eating normal food, they can expect to eat only about 3/4 of the amount they were habitually putting on their plate beforehand. That's quite important. They need to know that in advance. Those are all ways that we try and set up the most difficult phase. The most difficult phase is keeping the weight off in the long term. Because if you look at it biologically, you have the same person doing the same things in the same environment, fast food environment, an environment where it's become socially acceptable to eat when you're walking down the street, even, according to Hollywood, to eat when you're talking. Where did that come from? You see, the social change in the last 50 years has been astonishing around food, but that's all part of the obesogenic environment. It's not just the fast food and the availability of food constantly and the lack of satisfying nature of fast food. That's all part of it. But avoiding that and keeping your weight constant, that's a class act, and that's something that we don't have easy answers to. But people who are sufficiently motivated can certainly do it. So that at 5 years from our direct study, these are data that were presented at scientific meetings, they're not quite yet published, but I can say at 5 years, people were still very considerably below their starting weight. The average weight was still 6.1 kilograms below baseline. Now, for a dietary study at 5 years, that's never been achieved before. Now, only those people who kept off an average of 9 kilograms were still in remission at 5 years. But that says it all, because it's a matter of, yes, getting the weight off. But the human difficulty is one that I'm very alive to, and we're constantly working to try and improve this matter of preventing weight regain after this very successful method of losing weight.
What percentage was that, Roy, of the intervention subjects who were able to stay in remission and achieve that 9 kilogram weight loss at 5 years?
Of the people who are in remission at 2 years, it was 26% who are in remission at 5 years. But overall, if we look at the line up on the starting line, 149 people started off in the weight loss group. Then it was 11% of those 149 people. We lost track of some of them, but we still count them in saying 11%. If we stick to the information we know for definite, then yes, 13% were in remission. So, in round figures, around 12%. You might say, but that's not very good. Hey, if we use a drug, we talk about number needed to treat. And a number needed to treat that's quite good would be about 1 in 10, 1 in 12. So, if you use a drug, then 1 in 10 people are going to actually benefit from it for the reason that it's prescribed, to prevent a heart attack, for instance. But here we have a simple dietary, lifestyle information method that produces more than 1 in 10 of remission of a disease which causes terrible morbidity and early death. So 12% has got to be set in perspective, and it's good. It's not good enough. We can improve on this. But of course, that is a challenge for medicine and healthcare systems to use this information and to put it to good use.
Yeah, and that 11% or 13% is also not considering the potential benefits that people would have had who did enter remission, who are perhaps not in remission, but surely there is some benefit to improved blood lipids and improved blood glucose for a period of years when you're considering your overall risk of cardiovascular disease, for example.
Yes, I'm pleased you asked me about that, because this is one of the most dramatic findings. Again, as yet unpublished. I hope it'll be published in a few weeks' time, but it has been made public at scientific meetings. If we take that 149 people on the starting line for direct in the weight loss group, 149 in the control group, the risk of any serious illness was halved in those people that undertook the weight loss. So merely starting off on the weight loss, even though some people dropped out quite early, small number, but they did, the overall adverse event rate was half. Now, what was driving that? Well, there were a few less strokes. The numbers weren't large enough to show a difference in heart attacks. We had very few of those. But the main difference was in infections of all kinds, including leading to serious foot infections, and in new cancers. Now, in the people in the weight loss group, the number of cancers that they developed in 5 years was 1. And that was in someone who dropped out early and probably didn't lose weight. The number in the control group that were treated according to conventional best practice was 8. Now, these numbers are small, but hey, a ratio of 8 to 1 of new cancers that we know are related to overweight and obesity, that is a fabulous outcome of the direct study. So, yes, health benefits of weight loss are very considerable. And can I just make a jump forward to knock on the head a silly idea that's been around for a long time? Yo-yo dieting is bad for your health. That's nonsense. There's no consistent information that losing weight and putting it on is bad for overall health in the weight range we're talking about. So we can be sure that people who lose weight and keep it off for a while and over a period of time have reduced their average weight, they will gain hugely, and there will be not only healthier but also happier people.
To kind of double click on that concept of yo-yo dieting and coming back to this intervention. So just to be clear, when you looked at the 5-year data, and I think you said there was 26% of people that were in remission, or 26% of people in remission from 2 years were still in remission at 5 years. Is this still a group of people who only did that low-calorie intervention, that 12-week intervention that was 800 kilocalories a day, and they only did that once? They weren't repeating that over the years to come?
If they put on weight, they were offered the possibility of using the low-calorie products again. Because what we discovered in Direct was that people, of course, put on weight during times of stress due to family illness, due to financial reasons. All these factors kick in. And when someone is busy dealing with this, the matter of concentrating on food intake and keeping it down goes out of the window. So we found that the commonest reason for weight regain was a sudden event, which of course passes. And so when that event had passed, we offered people the chance to regain the previous advantage. So that was a process that was running in the background, and in Direct, half of all the participants needed at least one of what we called a rescue package. So yes, this is part of the business of avoiding long-term weight regain. And so if people put on weight, it's not a failure. It's just something to be dealt with. So yes, some people did have short periods of low-calorie intervention to get the weight back down again, but by and large, they were just living entirely ordinary lives, eating ordinary foods, trying to avoid fast foods, and keeping an eye on their weight.
I think you said 36% of the subjects in the intervention group in Direct achieved remission at 2 years, which is remarkable. That's an incredible result to see. But if we flip that statistic just for a moment, and let's think about the individuals. So let's think about the 2 out of 3 individuals who come back and are not in remission. So that's 64%. What are the main reasons that you believe would explain why they didn't achieve remission?
Well, it was really the weight regain that sticks out a mile. So the people who were in remission maintained their weight loss far better than the ones who relapsed. And so that was very obvious, for instance, at the 5-year mark, when the average for the whole group was a weight loss of 6 kilograms. But that was swayed, as it were, by the small group who were in remission, who was still at just under 9 kilograms, 8.9 kilograms weight loss. So if we look at the people who'd lost remission, my rough calculation would be probably about 5.5 kilograms below baseline, compared with 9 to stay in remission over 5 years. So that's how it stacks up. So that's the main reason. And of course, you could look for reasons underlying that. And life stresses are a big matter. Changes to social circumstances, etc. So these are things that affect real people, and as doctors, we just need to advise how best to navigate those. But I think having demonstrated the biology of type 2 diabetes, having shown what a simple condition it is in the managing concept, it helps doctors deal with all these complexities, because life is complex. And I wouldn't suggest for a moment that this was a simple matter for an individual to deal with, but we can see the main factors and deal with them. That's really the exciting consequence.
So how do you think about reducing your risk of, say, developing insulin resistance and type 2 diabetes versus treating or managing type 2 diabetes? Do you see the same dietary pattern that's best for reducing risk also being the same dietary pattern that's best for treating it? I know there's a bunch of research out there looking at different dietary patterns in type 2 diabetes, and lots of folks are sort of working or looking more through that low carb kind of lens. How do you sort of reconcile all of that, or think about this idea of managing risk versus treating the condition once someone has it?
Yeah, so I would say in general, a lot of the recommendations are similar, and a lot of those dietary patterns that I talked about, like Mediterranean, DASH, Nordic, Portfolio, they can be good for preventing and managing diabetes. And you'll see in a lot of clinical practice guidelines that you'll see similarities for prevention and treatment. I think when you get to actual type 2 diabetes, that's when more individualized care and blood sugar management is going to become more important. And in those scenarios, you will see that perhaps having less carbs or choosing different types of carbs like low glycemic index can become particularly important.
Right. And then if we consider, I guess, the importance of weight loss in trying to help get someone into remission, I always go back to the kind of the weight loss trials and low carb versus high carb, and there doesn't really seem to be a clear winner, which then doubles back to the point you made earlier, which is going to be the sort of dietary pattern that you can follow, you can adhere to, and in this instance, if weight loss is a goal, which is going to be the one that feels the easiest, I guess, for you to do.
Certainly. Adherence is definitely probably the biggest predictor of success in most of these diet trials, particularly the weight loss trials. So I think that's really, really important, and maybe a low carb diet could be good for someone, but maybe for another person it's just not going to fit with their lifestyle.
The one thing I do think about often with the low carb diet, and I understand why some people choose it, because for them it does help with weight loss. And I had Christopher Gardner on talking about diet fits, and in that study, some people did do well on low carb and some did well on high carb. It's very possible to have someone who does lose weight on a low carb diet for sure. But I always kind of come back to the construction of that low carb diet. So with all of the research that you're doing, and I know we sort of jumped into this off carbohydrates, so I haven't lost the train of thought. We're going to keep going on fats and protein, but this sort of fits here because we're talking about low carb diets. With your research and understanding of particular nutrients and cardiometabolic health, if someone's choosing a low carbohydrate diet, is there a way that you would construct it such that it would also be reducing their risk of some of these cardiometabolic sort of conditions in the long term?
Yeah, certainly. I think some concerns that can come up with low carbohydrate diets is if you are basing the diet on like higher saturated fat foods, so quite heavy in maybe red meat and butter and some other animal products. And we do know that diets that are high in saturated fat can increase LDL cholesterol. So I think that's something we need to be mindful of, especially if we're talking about diabetes. They are at an increased risk of heart disease. So we definitely want to keep those cholesterol levels low as well. So I think it's important that you kind of limit saturated fat in your low carb diets, and you can focus more on some plant sources of fats particularly, and then making sure you get enough vegetables as well, and some plant protein sources. And I think Dr. Jenkins has done some interesting studies looking at low carb vegan diets specifically. So you might be familiar with his Eco-Atkins study that was quite a while ago now. I think it was in 2009, but he compared a low carb vegan diet to a higher carb vegetarian diet and saw reductions in LDL cholesterol and ApoB. So I think if we base those dietary patterns that are lower in carbohydrate on more plant sources, we can control all of your risk factors that are important for cardiometabolic health.
I guess for someone who maybe is going through this, to consider is that you can shift a lot of these biomarkers in a favorable direction if you're losing weight. But the research, at least that we have today, suggests that you're not going to keep losing weight. You're going to get to weight maintenance, and many people end up actually regaining weight. So at some point in time, the kind of nutrient makeup of the diet does matter a lot.
Exactly. As you mentioned. So with weight loss, of course, you will see some beneficial effects of weight loss, but as we mentioned, it does plateau, and you can have increased risk factors like LDL cholesterol even when you're losing weight as well. So it's really important that we fine tune some of these dietary patterns.
By definition, what is non-alcoholic fatty liver disease?
So the diagnosis of non-alcoholic fatty liver disease is when there is an accumulation of excess triglyceride or excess fat in over 5% of hepatocytes or liver cells. And for the non-alcoholic component of this particular condition, it's that the accumulation of that triglyceride is not related to excessive alcohol consumption, which, depending on the definition applied, is typically related to less than 20 grams of alcohol. So in that type of context, then it is an emphasis on more dietary and lifestyle factors, for which there are a number of non-modifiable and modifiable risk factors, as there are for any of these chronic non-communicable conditions that we are particularly interested in for nutrition. But that's the general definition: net accumulation of excess triglycerides in over 5% of hepatocytes, which is not due to excessive alcohol consumption, with the threshold for alcohol typically set for this context at about 20 grams.
So hepatocytes equals liver cells, just to clarify that. I know you did there, but that's going to come up quite a lot in this episode, no doubt, just so that no one is confused there. So it's possible to develop fatty liver disease from excessive alcohol consumption. It's also possible to develop fatty liver disease through other lifestyle exposures. And then these are captured under this definition of non-alcoholic fatty liver disease, which to my understanding is the most common cause of chronic liver disease. And that's what we're focusing on today. So who is this disease affecting within our population, and approximately how common is it?
Like you said, it is the most common form, and current estimates in terms of global estimates suggest, give or take, around 25% of the population may exhibit fatty liver. And there's a really high correlation within that with the overall metabolic syndrome, i.e. a constellation of cardiometabolic risk factors that are related to increased hepatic fat. So although that's a kind of average global estimate range, depending on the population, there are estimates that prevalence may range from, say, 12, 13% to up as high as 40%, depending on the specific population and subgroup you're looking at. As far as the risk factors that are related to NAFLD, in terms of non-modifiable risk factors, there are some sex dimorphic differences. So differences in terms of fat metabolism and fat accumulation, in terms of where fat accumulates in the body, the distribution of accumulated fat between males and females, that ultimately confer a higher risk on males. There are ethnicity differences where individuals from South and East Asian ancestry or Hispanic ancestry exhibit a higher prevalence of and greater risk for fatty liver compared to Black or African American ancestry, if we're looking at American data, or in the UK, for example, Black Caribbean ancestry compared to white Caucasian populations. So there is a kind of a clear divergence in risk related to ancestry or ethnicity as well. And then there are particular genetic variants. So all of these kind of non-modifiable factors can relate to risk. In terms of the modifiable factors, and much of this relates to the non-modifiable factors. For example, like I said, the reason that there are sex differences and even ethnicity differences in risk may relate to, for example, predisposition to visceral fat accumulation. So central adiposity and visceral fat accumulation, highly indicative of this kind of cardiometabolic risk profile that correlates with increased fat accumulation in the liver, inactivity, and of course diet. And within diet, there's a hierarchy, and we can obviously tease this out over the course of the episode, that generally relates to overall energy intake and excess. But then secondary to that, there are some really interesting aspects to this overall evidence base that relate to dietary composition, and of kind of most research interests, at least historically, was focused on components of added sugar, such as dietary fructose. More recently, an emphasis has shifted to look at the composition of dietary fat. And so within that, there's a kind of second level in addition to total energy intake, there's a second level influence of macronutrient composition of the diet. And there is a relationship between that macronutrient composition and energy intake as well, such that even at levels of relatively maintenance energy or energy balance conditions, we can actually see differential effects of various macronutrient subtypes. So as far as that overall, kind of picture of modifiable risk factor goes, diet and physical inactivity, because they are obviously then going to relate to central adiposity, visceral fat accumulation, and ultimately the accumulation of fat in the liver specifically.
What does hepatic fat oxidation mean if someone's hearing that for the first time?
So the fancy it is the fancy way of saying the utilization of fat in the liver. So that's actually something we really should kind of highlight. When fatty acids present to the liver, there are typically two primary fates, so to speak. One is esterification, and the other is known as beta oxidation or oxidation. So explain essentially what both of those really entail. Esterification is the fancy term for the creation of new triglyceride. Three fatty acids bound together with a glycerol backbone, right? The primary form of fat in the circulation other than free fatty acids. And of course, the primary form that we consume fat through our diets in. So esterification, listeners should think that's the process of creating new fat in the liver. Of course, that's going to be, important to this retention and accumulation of fat in the liver. And then beta oxidation is essentially the pathway of producing energy from fats in our diet, what we would colloquially term as burning fat, so to speak. And so within that pathway, you're talking about the actual utilization, the processing of fatty acids down the pathway of oxidation, is to say that those fatty acids are being utilized in the production of energy. And as a result, they're not being stored. So when we use the term hepatic fat oxidation, we're talking about the actual utilization of fatty acids for the production of energy in the liver, which means they're not, as a corollary, being stored in the liver. And we know from stable isotope tracer studies that there is a sex difference in the ability to oxidize, to utilize fatty acids, and that the liver's ability to do that is greater in women compared to men. Whereas men typically have a lower rate of utilization of fatty acids or oxidation of fatty acids, and potentially then obviously then have a greater partitioning of fatty acids into the other pathway, which is esterification and storage within the liver, which leads to this increase in the production of triglycerides and triglycerides in VLDL.
Can I throw a little bit of that back to you and just see if I've caught all of that? So there are some differences between genders and ethnicities that will predispose certain people to accumulating fat within the liver, and also increased triglyceride production in the liver. This is a problem for a few reasons, and I think we can unpack this. I'll throw a few things out and get you to elaborate on it. But one of these is that one of the liver's jobs is to produce glucose, and it distributes that through the body through circulation. That stops us becoming hypoglycemic. But my understanding is when we're accumulating fat within the liver, we are developing insulin resistance in the liver, and insulin's job at the liver is to sort of shut down or slow down that glucose production and glucose pouring into circulation. So as the liver fat concentration is increasing, you're losing that ability to sort of turn off glucose production, and the net effect over time can be an increase in blood glucose or less healthy blood glucose control. And then the other thing that you mentioned there is the liver is producing more triglycerides. They have to get packed into some type of vehicle to be transported. They're packed into these VLDLs, which are an ApoB containing lipoprotein. And if I'm kind of connecting a few dots here from my conversations with you previously and Thomas Dayspring, this can be a problem because the triglycerides, I believe, can increase the residence time of these VLDL lipoproteins, and you can get an increase in ApoB, which is then predisposing someone to cardiovascular disease. Does all of that sound accurate, or have I missed something there?
No, that is, and obviously you've introduced the glucose component now as well, which is of course important. So as the liver gets fatty, there are a number of metabolic and cardiovascular consequences of that. One is that we typically see in elevation in circulating non-esterified fatty acids, free fatty acids, that relates to insulin resistance in the liver, influences insulin resistance in the liver. There is obviously this upregulation of VLDL and triglyceride. And as the liver is becoming insulin resistant, the normal response to an individual consuming a meal containing carbohydrate is, if they were in the fasted state before that meal, the liver would be the primary site of glucose production and release to maintain, blood glucose levels within the normal ranges. And then to consume a meal in an otherwise healthy individual, there would be, via the action of insulin, a suppression of hepatic glucose, of liver glucose production and output, so that the body can deal with the now exogenous or dietary external source of glucose that has come in. Once the liver is insulin resistant, that process, part of the resistance to the signaling of insulin, is that suppression of liver glucose output is also impaired. So the liver continues to export glucose. And this is why this really is an overall clustering of cardiometabolic risk factors together that are all influencing the potential cardiovascular and metabolic consequences of fatty liver. So they're both of those components are important. And yes, the sex differences appear to relate primarily to this sex dimorphism in sex steroids and their respective influence of androgens and estrogens on the site, the distribution of adipose tissue, and the related metabolic functions of that adipose tissue. And then ethnicity differences may relate to a number of factors. There, for example, higher prevalence of certain genetic polymorphisms in, for example, Hispanic populations. There's also the fact that BMI, when we're looking at BMI, for example, the actual cutoff points differ relative to ethnicity as well. So, for example, if you're looking at a South Asian population, while typically we would define using BMI overweight as between, say, 25 to 30, and class 1 obesity as 30 and over to 35, that's actually lower in Asian populations. And so, for example, overweight would be classified as between 23.5 to 27.5, and class 1 obesity would be classified as over that 27.5. So if you were taking two people, one, if I'm in the UK, for example, I take someone from white British ancestry and someone from British Indian ancestry, and they both have a BMI of 27, that means different things for how we would interpret that relative to adipose tissue distribution. And that often may mean that there is risk present at BMI thresholds that if someone's not thinking about some of these ethnicity specific cutoffs, they could be missing that. And so in that context, for example, other metrics can be particularly useful here, waist circumference in particular, because you could have someone who, for all intents and purposes, has this quote normal BMI, but they may still have visceral fat accumulation and hepatic fat accumulation, and then of course related to that is components of diet as well. So they're the kind of broad brush difference or kind of factors influencing differences both between sex and between different ethnic backgrounds. But there's obviously some debate over whether some of those ethnicity specific cutoffs are even themselves a bit arbitrary. And there are some calls to refine further where the best kind of diagnostic cutoffs might be.
So my understanding, at least when it comes to type 2 diabetes, is that about 5 out of 6 people with type 2 diabetes are in the kind of overweight or obese BMI classification, and then 1 out of 6 are considered normal, which was what Roy Taylor was looking at in that study. And I think part of the rationale, if I remember reading correctly, was that there had been some debate around, well, maybe people who are getting type 2 diabetes who are a quote unquote normal BMI, maybe the etiology, the cause of type 2 diabetes for those people is different, something else causing it. And therefore maybe the intervention is different. When I try and sort of reconcile all of this, and again, I appreciate we're talking about type 2 diabetes here, so we can then think about non-alcoholic fatty liver disease separately, even though they're very related. It's that shared commonality across all of these people that are developing type 2 diabetes anyway, regardless of what their BMI is the accumulation of too much fat inside or organs, between organs, fat where it shouldn't be. And for various reasons, that's occurring in some people who are what we would describe as a normal BMI. It's not the majority of people. And then for everyone else, it's occurring at higher BMIs, but common amongst all of them. And what seems to be driving the metabolic consequences is this fat that is finding its way into the wrong tissues. And Roy Taylor's most recent study kind of highlights that there's also a shared intervention, that if you can adopt a hypocaloric diet, hypocaloric meaning less calories than your body sort of requires to maintain its weight, and you can do that in a way where you are able to reduce your total body weight by enough such that you get the fat out of the wrong places, then you can begin to kind of unwind some of these metabolic derangements that are occurring. And in many people, if they haven't had that condition for too long, go into what's described as remission. Do you think that is similar for non-alcoholic fatty liver disease, in that the majority of people that develop this are probably overweight or obese, but there could be a kind of lean phenotype or a person who have normal BMI that gets non-alcoholic fatty liver disease, and without having the study, I don't believe there's been a study looking specifically at this with non-alcoholic fatty liver disease, but do you think it's the same scenario where, regardless of that person's BMI, if they adopt a hypocaloric diet and lose enough body weight, they can get the fat out of the liver and reverse the non-alcoholic fatty liver disease to the point where all of those biomarkers and diagnostics sort of return to normal levels?
Yes, I mean, I think what you're describing is an overarching commonality that may encapsulate the drivers of metabolic disease overall, and so it's almost at a level of principle that that description is accurate, and obviously then the kind of specifics may differ, relative to what exactly we're talking about, between, say, for example, fatty liver versus type 2. But as an overarching unifying principle, that we have the excess accumulation of fat in the liver, driving hepatic insulin resistance, contributing to an increased concentration of circulating free fatty acids, particularly in the postprandial period or in the period after a meal, therefore influencing new triglyceride synthesis, impairing the clearance of triglycerides in the postprandial period or post-meal period. And so, you mentioned that Guy and I used the term, energy toxicity. We have this term, lipotoxicity, which is really characterizing all of that as an umbrella term for all of those factors that I was just describing. This increase in flow of fats to other tissues, which then drives, the increased inflammatory profile of adipose tissue. If we're talking about these visceral depots, liver depots, immune responses, oxidative stress, and so this is potentially present in individuals at different levels of BMI, and would imply that the intervention, and we know from the body of available intervention evidence on hypocaloric diets, like we alluded to earlier, that macronutrient composition is secondary to the restriction of energy intake, will allow for that clearance. And we do know that there is, individuals can be characterized by fatty liver in the absence of a BMI in the obese categories range. So, to your point, does the similar proposition offered by the Retune study apply in the context of fatty liver? Overall, we would say, I think, from the body of evidence, that it does.
So how much overlap is there between non-alcoholic fatty liver disease and type 2 diabetes? And is it possible that someone is diagnosed with non-alcoholic fatty liver disease, but they don't have type 2 diabetes because their pancreas is, able to sort of compensate and just produce more insulin, and they're able to kind of keep their blood glucose within the normal range despite the excess fat that has been accumulating in the liver and the insulin resistance there?
Yes. So it is possible that an individual have fatty liver without necessarily a diagnosis of type 2. So conditions can exist independently. But in terms of, I guess, the modern, because of course, type 2 diabetes can itself be influenced strongly by genetic risk factors, can occur at kind of normal weight BMIs, etc. Both can exist independently, but in the context of, what we're dealing with in the population now, with the abundance of excess energy, etc., the correlation between the two is particularly strong, and they may coexist. And the coexistence of fatty liver and type 2 diabetes is associated with, an overall worse risk profile, a metabolic profile, than simply having either alone. In terms of overall prevalence, of the correlation, of the coexistence of the two conditions. There was a meta-analysis in 2017 that suggested, on average, the pooled prevalence was just about 60% in terms of the association between fatty liver and type 2 diabetes incidence. But the actual individual study estimates ranged and were, in some studies, I think the highest prevalence of the coexistence was 87% in one study. So, but again, the average prevalence in the analysis was about 60%. And if we're talking about the overall, we've been discussing a lot the kind of under the hood kind of mechanistic stuff here. It's unsurprising. We know, obviously, we've touched on this, but to kind of circle back to, I guess, re-emphasize and cement it in listeners' heads, if the liver becomes fatty, the liver becomes insulin resistance. That resistance to insulin then impairs the suppression of liver glucose production that would occur in an otherwise healthy individual that's just consumed a meal. So you get increased fasting glucose levels, you get elevated insulin levels. You've got, obviously, the exacerbation of overall insulin resistance and even skeletal muscle insulin sensitivity from continually elevated circulating fatty acids, and indeed the accumulation of intramyocellular, so the accumulation of fat in muscle cells, all influencing, the overall kind of state of insulin resistance. And then, of course, there is this lipotoxicity we mentioned briefly just there, where this excess accumulation of fat in the liver and in visceral organs starts to spill over. And this can include the pancreas, and the pancreas itself can start to increase its fat depots. And the consequence of this increase of fat in the cells of the pancreas is to impair the signaling pathways associated with with insulin function. The defective ability for insulin to and the beta cells to produce and release insulin, and so you get this progressive decline in the capacity of the beta cells to function, and that's the primary hallmark characteristic that predates a diagnosis of type 2 diabetes. So you've got elevated glucose factors or hyperglycemic factors. You've got elevated insulin factors and elevated insulin resistance in the liver, all complicated by fatty liver. You've got this relationship with circulating lipids, non-esterified or free fatty acids, and elevated triglycerides, all kind of interacting, where the presence of fatty liver can drive the progression of type 2 diabetes. And there are kind of little available pharmaceutical interventions that are specific to fatty liver. Some diabetic drugs can have kind of, it seems, effects, but really the capacity to exert a kind of reversal of the levels of fat in the liver to normal ranges is very much something that can be influenced by diet, of course, energy balance within that, and specific nutrients then secondary to energy balance, and physical activity as well.
There's another study, Richard, that speaks to your point about the combination of saturated fat and fructose possibly being the kind of double-edged sword, the worst case scenario, I should say. And that was the sober cases. It was a 2010 paper, healthy male subjects, and they looked at three groups.
35% of calories from fructose, 30% from saturated fat, or 65% from both fructose and saturated fat. And they were matching the energy between those groups. And these were all hypercaloric, so there was a surplus of energy. And the fructose group had an increase in liver fat by 16%, the saturated fat group by 86%. But then when you combined fructose and saturated fat, it was 133%.
Right. Yeah. So, I mean, I believe that when you go on saturated fat, that there's enough fructose in the system to really, there's still probably enough fructose in the system that the saturated fat is just going to drive that fat up in the liver very quickly. And if there's no fructose, it will still drive the fat up, but maybe not as much. So the 86%, what we don't know is how much, fructose were they actually eating, and, was there fructose being produced in the liver? But it for sure, the data shows, in terms of the practical thing for our diets, that saturated fats can increase fatty liver pretty significantly, probably more than just sugar, when sugar is given with a low-fat diet.
What's the interaction there? So from a mechanism point of view, if you were going to hypothesize, I appreciate this might not be fully understood, but what is it about, say, fructose sort of interacting with saturated fat to make saturated fat more deleterious in terms of this liver fat deposition?
Okay, so fructose, remember, generates intracellular uric acid, and fatty liver is really linked with intracellular uric acid levels. It's been shown in like hibernating animals and all kinds of things where the hepatic uric acid really is a good marker for how much fat is in the liver. And fructose increases it. Saturated fats increase it a little bit, but the combination really drives it up. Now, interestingly, one of the things that's, is, how does saturated fat raise uric acid, and how do fats do? And there's some data that, ketosis can raise uric acid, but there's also data that when you start getting fat, adipose fat, that kind of creates a local hypoxic state, or a local area with low oxygen, which stimulates uric acid production. And so there is this interesting thing where fat itself may drive uric acid production, and lowering fat can lower uric acid for sure. So there is a relationship of fat with uric acid. I mean, there were studies done many years ago showing that putting people on a high-fat diet can raise their uric acid levels. And so, I was looking to see the saturated fat increase uric acid more than polyunsaturated fat. I couldn't find any data on that, but I do know that, like in our study where we gave saturated fat, we measured hepatic uric acid, and it went way up with the combination. So it could be that. And the way the uric acid works is it causes oxidative stress to the mitochondria, which is the energy factories. And then that actually stimulates fat synthesis and blocks fat degradation. But, when you're eating fat, you also can, just the fat itself can end up in the liver just from eating a lot of fat. There's some evidence that might be a mechanism too.
I want to come back to kind of zoom out and sort of make sense of this from a very practical level for the listeners. But something else that I do want to touch on is the type of fat, because you've mentioned a couple of times a high-fat diet has done this, and there does seem to be this kind of anti-polyunsaturated fat type rhetoric online, and I can't personally make a lot of sense of it. And when I was looking through a lot of these trials with you, I was finding some pretty fascinating results. And there's a couple studies here I'd like to go through, because it seems that when it comes to hepatic fat, that the type of fat matters a lot. And there was a study, and I'd like to discuss with you, and you sort of spoke about uric acid before, but if there's potentially other mechanisms here at play. The Bajermo 2012
paper. I'm not sure if I pronounced that correctly, but BJERMO. It was a 10-week study, 67 odd participants that were abdominally obese adults, and really neat. They randomized them to a high saturated fat or a high polyunsaturated fat diet, and that polyunsaturated fat diet was mostly omega-6 fats, the ones that tend to get demonized the most. And the goal was weight maintenance, but they did put on a little bit of weight. It was under a kilogram, but over the 10 weeks. And in the saturated fat group, liver fat went up by 7% relative to baseline. And in the polyunsaturated fat group, it went down by 9% relative to baseline. And these researchers were also interested in looking at inflammation and oxidative stress. And so online, you'll hear quite regularly that omega-6s are bad when it comes to inflammation and oxidative stress, but they found no increase in either of these in the polyunsaturated fat group. And their conclusion, which I have here, was that compared with saturated fat intake, omega-6 polyunsaturated fats reduce liver fat and modestly improve metabolic status without weight loss. A high omega-6 polyunsaturated fat intake does not cause any signs of inflammation or oxidative stress.
Yes, I agree with you. So let's just go back. I believe fructose is really playing a big role in driving metabolic syndrome, but it works best when it's given with fat to make works best, meaning creates the most fat when it's working with a high fat diet. But the type of fat really makes a difference. And when it comes to calories, fat is all 9 calories or so per gram. But when it comes to the type of fat, it really does seem to make a difference. And saturated fat really seems to be the worst culprit. And when you compare it to polyunsaturated fats, the saturated fat diets that when I've seen this, like the study you talked about, which is a great one, the saturated fats tend to cause more a worse fatty liver, evidence of more inflammation, a greater rise in LDL cholesterol, all the bad things. So saturated fat tends to be worse. And you're right that, there's some data that omega-3 fatty acids can really, like help block fructose effects. And there are all these studies. I've never done one of these studies, but there are lots of studies suggesting that omega-3 is really good. And that led to this concept that the omega-3, omega-6 ratio is really, really important. And these days, a lot of people are eating seed oils that are rich in omega-6. And so there's all this stuff in the internet saying that the omega-6 is really a big problem. But if you actually dive into the literature, there's not so much evidence that omega-6 is doing anything, bad compared to, other fats. Like saturated fat looks like it's the winner for being the worst loser. It's saturated fat appears to be the much worse than polyunsaturated fats, and monounsaturated fats like olive oil seem to be pretty healthy. So my guess is that that polyunsaturated fats are getting a bad shake, and that omega-3s clearly look beneficial. Omega-6, most studies suggest that they're not as bad as people are saying. But saturated fats, when you take a diet high in saturated fats, you're going to get into trouble. It's going to cause fatty liver. It's going to, it's going to raise your LDL. It's going to be associated with atherosclerosis and increased risk for heart disease. So we do need to restrict our saturated fat.
Yeah, I think, beautifully summarized. I think that where some of the confusion comes, and I can sort of understand how someone could be confused by this, is that there's a difference between an omega-6 fat sort of on its own and the effect it has on health versus where a lot of omega-6s are found, which is in ultra-processed foods, which is a whole food matrix. And we know that ultra-processed foods are deleterious for health, but they're
there are many things in those foods other than the seed oil, which does show up on the label, but they lack fiber, they lack protein, they lack water, they have often added glucose and fructose. So,
and salt.
So there are many reasons why they're probably hyperpalatable and leading to the poor health outcomes, or associated with the poor health outcomes that we see. This is great, Richard. You've clarified a lot of things for me. Quick question on future studies. So let's say there's a study that comes out, because from what I'm hearing, you're saying background fructose intake is really the problem here. It's causing this reduction in ATP, and I'm curious, would you have to change your hypothesis or the way you're looking at this if you saw a study on healthy adults who had a low fructose background diet that were fed high saturated fat and their liver fat increased substantially?
Yeah. It seems like you're being a little sly here.
I'm not trying to sneak in a study. I'm just curious, as opposed to if in the future a study like that did come out, would that would be a little sly if somehow I pulled out a study that was published last week. I can assure you I'm not doing that. All these studies we've exchanged on email and spoken about. So
yes.
There's none of that.
Well, if you're So I think that saturated fats can increase fatty liver in the absence of fructose. I really believe that. We did a study with a fructose knockout mouse where it can't metabolize fructose. And if I give it butter fat, it will get fatty liver. Not much inflammation, but it will get fatty liver. And so I do believe that fats can drive fatty liver. I don't know if they drop the ATP level. And and as we mentioned, fat could potentially increase uric acid, which actually will help drive the ATP down. So it could still be a low ATP state with just fat alone. So it may be that fructose is not the only thing that can activate the switch. It's possible that saturated fat may have some effect as well. The fact that saturated fat alone can cause some insulin resistance would be supportive of that. And evolutionarily, eating saturated fat might be a good way to increase your fat stores. So, it might engage some of these same pathways, and perhaps it's through its ability to raise uric acid. So, I think that we have to be open, and my work and the work of my collaborators is based on our, interpretation of the data that we've done, and we're open to modify the hypothesis for sure. But, it does look to me like all these metabolic diseases are really energy disorders where we're dropping the energy in the cell. And if we can stimulate the energy ATP levels to go up, we can really make a difference. And this is why exercise is so good. This is why, reducing the bad foods will help. And it isn't just sugar, it's high glycemic carbs. It's really salty foods. It's, alcohol will do it. And and some of these umami foods like liver, organ meats, processed red meats. And, so there's a lot of things that can do it.
Do you think, it sounds like it's not really an even playing field. Like some people are dealing with heightened hunger relative to the next person.
Right.
Is it that you put on weight and then as a result of that you become leptin tolerant, or is it that, be it genetics or other reasons, certain people are just more leptin tolerant or have less GLP-1 sensitivity from birth?
Yes. No, this is a very good question. And we tend to believe these days that, and this is our culture out there, right? That there should be no differences, everybody is equal, and we are equal, and right. But in terms of our genetics, we are so similar, but also so different, right? Some of us have a predisposition, right, to be more obese or to be less obese, right? Or predisposition to develop diabetes. Even if you have obesity, I mean, let's go deeper, if I may, right? Not each and every, and we have realized that not each and every obesity is also the same. So some of us have more or less storage space in their adipose tissue. Mm-hmm. All of us have the subcutaneous adipose tissue.
I've heard people describe that as a personal fat threshold.
There is a threshold, right? So some of us have a small storage space. Like think about your apartment, your house, right? And you have your storage room, right? Some people have little storage space. Others have plenty of it, right? So for those of us who are fortunate to have a lot of storage space, potentially, in our subcutaneous adipose tissue, you can store their fat. Your body weight can increase. And to the extent that fat remains where it is supposed to be, in the subcutaneous adipose tissue, you have no medical problems.
So if it stays in the storage room, not a problem.
Not a problem.
But if it's overflowing into the living room and the kitchen,
that's when you start creating problems.
Right.
So about 22% of people, especially women, may be slightly more obese. If fat is not spilling over in other organs, we call them metabolically healthy obese. Could be chubby or obese. There is no problem, no need to treat them, right? But if the fat goes where it should not be, liver can cause fatty liver disease, can cause cirrhosis and liver failure, death over a period of decades, right? Not over a period of months. If it goes to muscle, it causes insulin resistance for people who are predisposed to develop insulin resistance. And the longer and the higher the degree of insulin resistance, the higher the risk to develop diabetes. If it goes to our vasculature, it's the same process. Atherosclerosis. It goes to our brain, right, and causes inflammation, neurocognitive decline, Alzheimer's.
So you got to keep fat out of the muscle, fat out of the arteries, fat out of the liver, fat out of the brain.
And right. And the very first, right, and most indicative marker is the belly fat, intra-abdominal fat, right? So if you see intra-abdominal fat, you know that most probably you have fat in muscle, you have fat in the liver, you have ectopic fat.
Other than just observing someone, is that something that you would become aware of through doing a blood test and looking at biomarkers, or is it a scan?
Yes, that's beautiful. That's a beautiful question. So this is work in progress, right? So we started several years ago with a crude indicator, BMI, body mass index. And this was started by insurance companies, Simon, because they had an interest and they still have an interest, right? So BMI is a simple crude index correcting weight for height. But we realized that this is not, as we realize what is happening, that this is not reflecting ectopic fat or, right? So then we started looking into waist circumference.
Which is a little bit more specific to like body fat distribution.
Exactly, little bit more specific, right? But again, different races have different numbers. And they tend to have, say, Southeast Asians, they tend to have lower BMIs. But for a lower BMI, they don't have a lot of subcutaneous tissue. They accumulate fat in the stomach. But still is not the best, right? We need to refine it. So now, inexpensive markers, right? We correct waist circumference for height. We have to correct it, right? Because the waist circumference depends also on height, right? But if one wanted to be even more specific, We now know which are the hormones that are secreted from overall fat, and this is leptin. You gave it the hormone leptin from the Greek word leptos, meaning thin. We are talking about obesity, but I can explain to you about what happens in anorexia nervosa or thin people, right? Because these are mirror images. And there is another hormone that we have done a lot of work on, is called adiponectin. And adiponectin reflects the intra-abdominal fat. And this is a hormone and an inflammatory marker, anti-inflammatory marker. And the more the intra-abdominal fat, the lower the levels of this hormone. The higher the risk for diabetes and fatty liver disease and cardiovascular disease. So you can measure it.
So the more intra-abdominal fat,
the lower the levels of this beneficial protective hormone.
adiponectin.
Yes.
And you can request that on a standard blood test?
Most laboratories should have it. The big laboratories have both of them. It's not yet standard biomedical practice, but we are getting there. It's research that is becoming practice. But if you go to LabCorp, or I don't want to advertise any, the big national laboratories, they can measure it. Now, you mentioned about scans, right? MRIs or CAT scans. Yes, we can measure it. With CAT scans or MRIs, we can measure not only how much fat you have, but also whether the fat is in muscle or in the liver. Mm-hmm. And they're pretty accurate. The problem is that they are expensive. Mm. So you cannot do it many times. You cannot follow people with that. You can break the bank, right?
What do you think about a DEXA scan or liver ultrasound?
Yes. So the liver ultrasound, and there is several companies that are making ultrasounds for the liver, is very specific, but not sensitive enough. So if you have more than, let me start by saying that a normal person should have no more than 5% fat in their liver. So the ultrasound is very specific if the amount of fat in the liver is more than 30%. Between 5 and 30% is a gray zone that is not pretty good in picking it up. So if you have a lot of fat, the ultrasound will find it. But if you have between 5 and 30%, is not as good as an MRI or measuring it.
So that makes it not a great option for
not a great option
for a lot of people who might be on the fence.
No, we are not using ultrasounds these days for fatty liver disease.
And DEXA?
DEXA scan is pretty good in terms of overall fat. We don't have it. It's not available like everywhere. It's not as expensive as an MRI, but more expensive than running a hormone. Cannot tell us a lot about which organ has fat or not, but it can tell us the overall fat mass. Yes.
So if someone's kind of listening and they're just thinking, I'd like to generally know where my metabolic health is at. Waist circumference to height ratio.
Yes, for sure.
And any particular blood biomarkers that you would also want them to look at?
If a laboratory has adiponectin, I would run adiponectin. Another very simple measurement is triglycerides over HDL ratio. So if you start having ectopic fat and insulin resistance, your triglycerides keep going up. And the good cholesterol, HDL, starts going down. So this is a red flag.
Okay, so triglyceride to HDL ratio, waist circumference to height ratio.
This is how I would be starting. And then if you see that these are abnormal, if you see your primary care doctor and you see these are abnormal, I would run a panel, right? The full cholesterol profile, glucose, right? One by one, right? The diseases that we know of, right? There is non-invasive tests like FIB4 for fatty liver disease, uric acid for arthritis, right? And you name it, right? So your doctor will prescribe these.
Ectopic fat, just to define that for the listener. So that's fat inside an organ?
Yeah, so ectopic fat, I don't like this as someone who is of Greek descent, but that's how we call it. Ectopic is, ec means outside of where it should be. I think dystopic should be a better word, if I can use. But this reflects fat in areas where it should not be. It could be inside an organ, like fatty liver disease, right? Muscle, or just intra-abdominally, in the abdomen. It shouldn't be there.
Which is visceral fat.
Visceral fat.
Gotcha. Okay. So really what we're talking about here when thinking about metabolic conditions is a problem that stems back to storing fat in the wrong place.
Exactly. And I'll tell you why. I mean, maybe I can spend 2 or 3 minutes describing more in depth. The process is generally the same. There is small differences, right? I will use liver as an example, but one can think also about the vasculature. It's the same. So if more fat goes to the liver than it should be, right? More than 5%, 5.5%, right? Our own body is programmed, is created in a way to defend physiology. So we realize without us thinking about it, our body thinks that, well, it shouldn't be there. I need to remove it. So what do we have, right?
Some sort of inflammatory response.
Yes. So we have macrophages. So macrophages go there to eat it up, to phagocytose. Trying to help.
So this is a repair effort.
It's a repair effort. And in this effort, it creates more cytokines and the inflammation goes up, right? There is a hot area, inflammation there, right? More macrophages, more cells are trying to remove it. If we help with diet and exercise, they will remove it and the inflammation will go down. But if this continues for months and years, then we go from fatty liver disease to steatohepatitis, which is inflammation, permanent inflammation. 20-25% of people who have more fat in their liver than they should will have steatohepatitis, permanent inflammation after 5 to 7 years. And another 25 to 30%, what happens with inflammation? It's like a lot of fire. Then you have burnt woods, right? You have scarring. And scarring, we call it fibrosis or cirrhosis. That's what it is, in essence. So the liver starts shrinking. And at the end of the day, you may end up with liver failure or needing a transplant. It's exactly the same in a way that happens. I'm oversimplifying, but I'm not inaccurate scientifically, right? Happens in the vasculature. So we have fatty streaks and areas with excess fat, inflammation, a fibrous cap, and then right, we may have occlusion of the vasculature and either strokes or heart attacks. So the process is the same. So in a way, at this point, we need to limit fat. This is the root of the problem.
So let's go further into the root of the problem.
Yes.
Where's that fat coming from that ends up in the liver?
Yes. So this is, we were designed, right? And we lived as humans, right? You know, our world has a history of 13 billion years, right? Our species has a history of hundreds of thousands of years. Most of our history, we lived in societies of scarcity, not affluence.
A lot of famine.
Famine. So we are programmed, right, to metabolize the calories we take in and store them. There was no refrigerators, no freezers at that point, right? So store them. So, and we are very efficient. And our societies of affluence are not making things easier, right? We have high calorie dense foods, right? We have more fat and lipids in our diet than we used to have throughout our history, right? And we exercise less. We have less demands. We don't burn as many calories as someone who is a farmer, right? Or a builder, right? Because machines are doing the work for us. So the energy balance is against us, right? So if we don't watch what we eat, right? And this takes time, right? Our brain gets used to it, right? And over time, we are leptin tolerant, and we develop more fat. And after we exhaust our storage space, it becomes ectopic fat and dangerous fat, right?
What
So we
explains
start
the
with
difference
diet.
between why one person can store more fat subcutaneously than the next person?
Yeah.
Presumably there's some
So
type of
we
genetic
are
difference.
genetically and epigenetically, we have different adipose tissues storage space, and this is differences between individuals, but also differences between ethnic backgrounds. I told you earlier that a BMI reflects overall obesity in Europeans or North Americans, right? But if you go to Southeast Asia, BMI has no relationship, right? People don't put a lot of fat in their subcutaneous tissue; they just put it direct in the abdomen.
Right, so for a given BMI, they'll store more weight.
Exactly. So for a given, say, percent fat, or for a given amount of fat, right, kilograms or whatever, they put it in their abdomen, intra-abdominally, not
which is why they have a different BMI classification.
That's why, this is why we are leading now to having different classifications, because lower BMI is more dangerous for certain people.
So if we think through that evolutionary lens for a moment here, you spoke to the fact there that throughout evolution, humans mostly have existed in an environment of food scarcity. So it makes sense to be really well adapted to store body fat. That helps you survive. Critically important to reach an age to procreate. That's what evolution cares about, right? Mostly. But is there an evolutionary advantage for storing fat viscerally, perhaps? Do you think?
I don't think so. There is an extra fat, right? The fat will have to be stored somewhere.
Where does the fat that ends up building up in the liver, where is that fat coming from? Is it just fat in the diet? Is it glucose being converted to fat?
Yeah. So for the liver specifically, like, it is coming from 2 or 3 sources. One is from the diet. Right? So the more, can I use the expression junk food one eats, right?
You can describe it however you want, Professor.
The more the liver is flooded into triglycerides and lipids, and they will be absorbed by the liver. So this is one area. The second area is, as we become more insulin resistant, this is where the vicious cycle starts, right? So we talked about fat being deposited ectopically in the muscle, causing insulin resistance. This insulin resistance mobilizes triglycerides and fat from our own normal subcutaneous fat, and creates more triglycerides in the bloodstream and is flooding the liver, right?
So the skeletal muscle insulin resistance precedes the liver build.
So this is number, right? And then there is a third step in this vicious cycle, right? The liver becomes insulin resistant, and it creates what we call de novo lipogenesis. Inside the liver, there is more fat created.
So this is, I guess, a downstream consequence, what I'm hearing, of genetics and energy toxicity. So too much energy.
Right. So our environment, right, builds upon our genetics. So genetics is given. So some of us are more fortunate, others are less fortunate. And the environment, right, what we eat, how we eat, like whether we exercise or not, right, where we live, is building upon it. And then it's a slow process, takes years. This is not going to happen overnight, right? It takes years.
Yeah, what's the average age that someone might develop non-alcoholic fatty liver disease?
It's the middle age. is the average age, is the middle age. But there is certain populations, if you think about it, like the Latino population, right? South America, they develop it earlier and they have more fat in their liver. So it depends. It takes about 5 to 7 years to go from fatty liver to inflammation, steatohepatitis, and another 7 years to go from inflammation to fibrosis, right? So it's a slow process.
Is fatty liver disease, I mean, at least it seems to me, in the literature, it's being written about more and more and more. Was, in terms of the world of metabolic conditions, was it less appreciated at the beginning of your career to now?
Oh, of course. So we'll come back to physiology in a minute. When we started, Simon, we did not know what this is. We would call it cryptogenic. Cryptogenic from Greece is crypto, is like, right, is hidden. And genic, genesis, right? The pathogenesis, the etiology was hidden to us. We did not know what we were talking about. It's a nice way to say we don't know anything about it, cryptogenic. And then we started realizing what it is not. So we called it non-alcoholic fatty liver disease. It was a negative. So people with who abuse alcohol, they may have a liver problem. We said, okay, this is something different. We did not know, right? And only recently, last year, we established the new term, which is metabolic dysfunction fatty liver disease or steatotic liver disease, right? So muscled.
It's one hell of an acronym.
Yeah. And this is work in progress, right? This is work in progress, but certain people felt that fatty liver conveys a certain stigma with it. So let's use again, like an ancient Greek word, steatotic, which is exactly the same, but does not have the stigma. So it's metabolic associated steatotic liver disease. Will change again. But this reflects, right, our changing appreciation of what is happening. No, this is what our students call it. So this is not established yet. But you may go. Right.
I thought that might embarrass you.
Yes, but we would like to have ideally, and we'll see whether this we get there. But a refined diagnosis, right? So we talked about what goes in, right? Let me explain also what happens inside the liver, right? And I'll come back to this, right? And I will surprise you with a couple of things. But so, okay, fat is accumulating in the liver, right? But we said one way to remove it is through macrophages and inflammation. And the other way is our mitochondria, which is the factory, the energy factory of our body, right? So we'll try to burn more.
In the liver. So mitochondria in the liver.
In the liver.
Okay.
So again, a balance, right? But how do we get there, right? So the elephant in the room, I use this expression, right, is obesity. Our society is obese. Okay, we know that, right? But not everyone who has fatty liver disease is obese. There is certain individuals, as you said earlier, right, more rare, that either they don't have subcutaneous adipose tissue, they're born without adipose tissue. We call them lipodystrophic individual.
That's the extreme scenario.
Extreme scenario. Generalized lipoatrophy. It's atrophic adipose tissue. Or their adipose tissue is destroyed during their life. An autoimmune process, like, lupus or arthritis, or medications people take for HIV. They develop a certain phenotype with lipodystrophy. So they have the same complications that someone has with obesity, although they are extremely lean. And why is this happening? Because it's ectopic fat. The fat they eat will have to go somewhere. If you have no storage space, even if you're lean, will go to your liver, your muscle, and create the same problems, right? there is a third group, right, out there. As we grow older, especially men, we develop sarcopenia. What does this mean, right, for the people out there? Our muscle mass goes down if we don't exercise, right? And this is a third factor that feeds into the problem. So we say that, okay, it's ectopic fat, but listen, in the future, if we want to treat it, we cannot treat an obese person the same way with someone who has sarcopenia. In someone who has sarcopenia, we need to give a medication or exercise to build muscle mass. Or someone who has totally destroyed subcutaneous fat, lipodystrophy, we need to give it different treatment. So going from muscled, we need to have subclassifications.
I imagine there's some overlap there too with a fair percentage of people with obesity as they're getting older also experiencing sarcopenia.
Overlap. They have sarcopenia and obesity. So there is a fourth group.
Over fat, under muscled.
Yes. So you will see, and I have not seen it, but if I had to bet, I don't bet, but I will bet, right? That in the future you will see a GLP-1 like medication bundled with a muscle building medication for people who have this overlap. And we need to know as doctors, right, which subgroup our patients fall into so that we give the appropriate treatment to the appropriate people. Does it make sense?
Hopefully bundled with some resistance training.
Of course. So everything, all the treatments, even the GLP-1s, the medications you mentioned earlier, right, they should be acting on a platform. And the platform is the appropriate diet and exercise. And pharmaceutical companies have been burned. As endocrinologists or metabolism doctors, we know that. You know that, right? But some people who built trials for the new medications for fatty liver disease were people who were not thinking the same way. They were approaching it from a success story of treating liver disease for hepatitis C or B, right? Hepatology or gastroenterology. They did not use this platform in the clinical trials. So guess what? They randomized people to one medication or the other, placebo, right? And they thought the medication would have spectacular results. Well, people who were taking the placebo, they did not see much improvement. So what were they doing? Improving their diet and exercise. And at the end of the 1 year of the 2-year trial, hundreds of millions of dollars, the two groups were so close that you could not detect a statistically significant difference. So everybody needs to be on a diet and exercise, and then you build with the medications. If you have someone who has hyperlipidemia or someone who has diabetes, right, we start with diet and exercise, and then you build with the medications.
We were talking about the Mantzoros classification when we were kind of clearing up some of the nomenclature here.
Yeah, so if this may stick as a name or may not, but in essence, this is going to describe the subgroups. That's how we call it, right? So it's a soup of acronyms, right? So we called it muscled earlier, right? But we said, well, we need to go deeper. So we need to have muscled lipodystrophy. We need to have SLD, sarcopenia. We need to have MS, SLD, so different subclassifications. And we are used to it in endocrinology. For example, a lot of people out there are familiar with diabetes or thyroid disease, right? So we talk about hyperthyroidism. But it's different to have Graves or autoimmune thyroiditis or other causes because you give different therapies. For diabetes, it's different to have type 1, type 2, you have 1.5, right? Give different therapies. So we need to have more refined classifications in the future. We're not there yet because we're still developing capacity now, but we'll get there. That's how I see it in the future.
There you have it, friends. I hope you enjoyed this episode. If you did and want to stay up to date with future episodes, be sure to hit that subscribe button on YouTube and follow on Apple or Spotify. Finally, thank you for showing up and the effort that you're making to take control of your health. I look forward to hanging out with you again in the next episode.